Hello there, and welcome to Science for Sleep, where curiosity slows down, thoughts soften, and science takes its time. Wherever you are right now, whether the lights are dim or the room is already dark, whether this is the end of a long day or the quiet middle of the night, you've arrived at a gentle place to wonder without needing to hurry anywhere afterward. Tonight's topic is one that feels both impossibly large and strangely familiar. Something most of us have looked at without fully grasping. Something that has followed humanity since long before calendars, clocks, or even written language. We're going to talk about stars, and not just in a poetic sense, but in a careful, grounded, quietly curious way. Specifically, we're going to explore a question that sounds simple at first, and then quickly becomes something else entirely. How many stars are in the universe, really? It's an innocent question on the surface. It sounds like something a child might ask while lying on their back in the grass, staring up at the night sky, counting the brightest points until they lose track. And maybe that's where many of these questions begin, not in laboratories or observatories, but in moments of stillness, when the sky feels larger than usual and our own thoughts get a little quieter. If you've ever looked up and felt that strange mix of comfort and smallness, you already know the feeling behind the question. It's not just about numbers, it's about scale and perspective, and the uneasy curiosity of realizing that what you can see is only a fraction of what's there. Before we drift any farther into that vastness, let me ask you something simple and personal. Where are you listening from right now? Is there a window nearby? Can you see the sky, or is it hidden behind clouds, city lights, or the soft glow of a screen? And what time is it where you are? Late evening, early morning, or somewhere in between where sleep hasn't quite arrived yet? It's interesting, isn't it, that a conversation about the universe always begins from a very specific place. One person, one moment, one quiet stretch of time, thinking about things that stretch far beyond any clock. If you find this kind of wondering calming, if it helps your thoughts slow down rather than speed up, you're always welcome to support this little space by liking the video or subscribing. It helps these long, unhurried conversations reach others who might also need a gentle place to rest their attention. But for now, there's nothing you need to do except listen. There's no quiz at the end, no facts you're required to remember. You don't need to hold on to every number or term. You can let them pass by the way clouds do, knowing they're there without needing to chase them. So let's begin where all good questions about stars begin. Not with equations or telescopes, but with the simple act of looking up. On a clear night, away from bright city lights, the sky doesn't feel empty at all. It feels crowded. Thousands of tiny points scatter across the darkness, unevenly, almost casually, as if no one bothered to arrange them. Some shine steadily. Others seem to flicker. A few have a faint colour if you look long enough. And if you've ever tried to count them, you already know how quickly the effort falls apart. You lose your place. You forget which ones you counted. Your eyes adjust and suddenly you see more than you did before. The number keeps changing even though the sky hasn't. This alone hints at the first quiet truth of our topic. Counting stars is not like counting coins on a table. It's not even like counting trees in a forest. The act of observing changes what you think you're observing. Your eyes adapt. Your brain fills in patterns. The sky you see at first glance is not the same sky you see after 5 minutes, or 10, or an hour. And that's before we even begin to talk about telescopes, which add another layer entirely. For most of human history, the stars were counted only by eye. Ancient cultures named the brightest ones, grouped them into constellations, told stories about them, and used them to track seasons and navigate oceans. But no one seriously attempted to count all of them, because it was obvious, even then, that the task didn't make sense. The stars visible from one place were not the same as those visible from another. Some appeared only at certain times of year. Others hovered so close to the horizon they were easy to miss. The night sky was familiar, but it was never complete. Still, humans have always had a habit of asking questions even when the answers resist us. How many? How far? How old? These questions don't come from a need for neat answers so much as a need to understand our place in relation to everything else. Asking how many stars exist is another way of asking where we are within the whole of things, and whether that whole is finite and tidy or sprawling and unruly. As science developed and telescopes grew more powerful, the night sky began to change. Not physically, of course, but perceptually. What once looked like empty blackness between stars slowly filled in with faint points of light. Smudges that had been dismissed as clouds or imperfections turned out to be something else entirely. With each improvement in technology, the universe revealed more of itself, and with each revelation, the original question became harder rather than easier. At first, it seemed reasonable to think that the stars we see are most of what there is. Maybe there are a few more too faint to notice, but surely they all belong to the same great structure. For a long time, that structure was thought to be the entire universe. Everything that existed was assumed to be contained within what we now call the Milky Way. In that picture, counting stars, while still difficult, felt at least theoretically possible. You might not do it one by one, but you could imagine estimating, extrapolating, getting close enough. Then came the realization that the Milky Way is not the universe. It's one galaxy among many. And that realization quietly transformed the question from challenging to staggering. If one galaxy contains hundreds of billions of stars, and there are not just dozens or hundreds, but potentially trillions of galaxies, the idea of a final number begins to feel less like an answer and more like a gesture in the direction of something vast. But even that isn't the whole story, because when we say the universe, we often mean something very specific without realizing it. We usually mean the observable universe, the part of the cosmos from which light has had time to reach us since the beginning of cosmic expansion. This is not the same as the entire universe. It's the portion we can, in principle, see and measure. Beyond that lies more space, more matter, and very likely more stars, but no information can reach us from there yet. So any number we arrive at will already come with a quiet disclaimer. This is how many we can see, not necessarily how many exist. This is where the question becomes interesting in a different way. It stops being about tallying objects and starts being about understanding limits. Limits of light, limits of time, limits of observation. When astronomers talk about counting stars, they're really talking about models, averages, distributions, and probabilities. They're talking about sampling small regions and using what they find there to make educated guesses about much larger ones. It's less like counting and more like listening carefully and inferring the shape of the room from the echo. And yet, despite all of this complexity, scientists do arrive at numbers. Enormous numbers, yes, but numbers all the same. They talk about tens of sextillions of stars, about figures so large that they stop feeling meaningful unless you pause and break them down. These numbers circulate in articles, documentaries, and classroom lessons, often delivered with a sense of awe, but rarely do we slow down enough to ask how those numbers were formed, what assumptions they rest on, and how stable they really are. That's what this long, unhurried exploration is about. Not racing toward a single dramatic statistic, but walking carefully through the reasoning that leads to it, understanding what we know, what we estimate, and what remains uncertain, letting the scale of it unfold gradually rather than all at once. Because when numbers get too big too fast, the mind tends to shut the door rather than open it. It's also worth noticing how this question changes depending on who is asking it. A child might mean, how many stars can I see? An amateur astronomer might mean, how many stars are in our galaxy? A cosmologist might mean, how many stars exist within the observable universe, given current models of galaxy formation and stellar populations. The words stay the same, but the scope shifts dramatically. Understanding the universe is not about forcing clarity all at once. It's about allowing complexity to exist without demanding immediate resolution. And if at any point your thoughts begin to drift, that's perfectly fine. You don't have to stay alert. You don't have to keep track. The stars have been there for billions of years. They're They're not going anywhere while you rest. This conversation will keep moving gently forward, from simple questions to deeper ones, without ever needing to announce that shift out loud. So with that, we've set the stage, a quiet place, a vast question, a slow path forward. The sky above us looks the same as it always has, but our understanding of it has grown deeper and stranger over time. Long before anyone tried to count stars, measure their distances, or name their types, humans were already looking up. Not out of scientific duty, and not because anyone told them to, but because the sky demanded attention in a way few other things ever have. Even today, with our lives packed full of screens, schedules, and artificial light, there is still something that quietly pulls the eyes upward when night falls. It doesn't matter whether you understand astronomy or not. The impulse comes first. The explanation, if it comes at all, follows much later. One reason humans have always wondered about the stars is simply because they are there, fixed above us, unreachable and yet constant. Mountains erode, rivers shift, trees grow and die, but the stars, at least on a human timescale, appear unchanged. The same patterns return night after night, year after year. That kind of stability stands out in a world where almost everything else moves, ages, or disappears. When something doesn't change, we notice it. When it stays just out of reach, curiosity grows. For early humans, the night sky was not a backdrop. It was an environment. There were no streetlights, no illuminated windows, no glowing screens to compete with it. Darkness was real and deep, and against that darkness the stars were sharp and unavoidable. Looking up wasn't a special activity. It was part of existing after sunset. The sky was as present as the ground beneath one's feet. That presence mattered in practical ways. The stars helped mark time. Certain patterns rose or set at predictable moments of the year, quietly signalling when seasons were changing. For people who depended on migration, hunting cycles, or agriculture, these signals were not abstract curiosities. They were survival tools. Wonder and usefulness were intertwined from the very beginning. You could admire the stars and rely on them at the same time, but usefulness alone doesn't explain the depth of human fascination. Many practical tools fade into the background once they become familiar. The stars never quite did. Even when their patterns were well known, even when their motions could be predicted, they retained an air of distance and mystery. You could navigate by them, but you could not touch them. You could name them, but they didn't respond. They were present without being accessible, and that combination is powerful. There's also something psychologically significant about looking upward. It changes posture, it changes breathing, it shifts attention away from the immediate concerns and towards something broader. Even today, people report feeling calmer or more reflective when gazing at the night sky. This isn't accidental. Human perception evolved in open environments where scanning the horizon and sky mattered. Looking up is built into us, not just physically, but emotionally. As societies grew more complex, the stars began to collect stories. Constellations formed not because stars are naturally arranged that way, but because the human brain is exceptionally good at finding patterns. Faced with random points of light, we connect them, draw shapes, assign meaning. A hunter, a bear, a river, a hero. These stories differed across cultures, but the impulse behind them was the same. When something is vast and silent, humans fill it with narrative. These stories did more than entertain. They anchored human experience in something larger. They connected daily life to the sky, reminding people that their struggles, celebrations, and losses unfolded under a shared canopy. In that sense, wondering about the stars was never just about the stars themselves. It was about belonging, orientation, and continuity. The sky became a reference point for identity as much as geography or ancestry. Even philosophies and religions grew upward. Many cultures placed their gods, ancestors, or afterlives among the stars. This wasn't because stars looked like homes, but because they were distant, unreachable, and eternal. If you wanted to imagine something beyond the limits of ordinary life, the sky offered a ready-made stage. Wonder naturally expanded into meaning. As observational tools improved, something interesting happened. The stars did not become less mysterious. They became more so. Telescopes revealed that some stars were not points at all, but clusters. That faint smudge wasn't a cloud. It was something enormous and distant. Each improvement in clarity came with a new layer of complexity. The sky didn't simplify under scrutiny. It deepened. This pattern repeats throughout the history of science. We often assume that understanding removes wonder. In practice, it usually multiplies it. Knowing that stars are suns, each with their own histories, lifespans, and endings, does not make them less fascinating. It makes the question of their number feel heavier, more consequential. You're no longer counting lights. You're counting furnaces of nuclear fusion, each potentially hosting worlds, each following a life cycle that spans billions of years. Another reason humans always wonder about the stars is because they sit at the edge of comprehension. The scales involved stretch the mind in ways few other topics do. Distance, time, energy, number. None of these behave the way they do in everyday life when applied to the cosmos. That stretching can be uncomfortable, but it's also compelling. It forces the brain out of routine pathways. It invites slower thinking. There is also a quiet humility embedded in stargazing. No matter how advanced a civilization becomes, no matter how much it builds or controls on Earth, the sky remains largely indifferent. The stars shine whether they are observed or not. That indifference can feel unsettling, but it can also feel grounding. It reminds us that not everything revolves around human concerns, and strangely, that can be comforting. Modern life has changed our relationship with the night sky in subtle ways. Light pollution has erased many stars from view for much of the world's population. In some cities, only a handful of the brightest stars remain visible. This loss is rarely noticed consciously, but it has an effect. When the sky becomes empty, the sense of scale shrinks. The universe feels closer, smaller, more manageable. But it's an illusion created by brightness, not reality. When people do encounter a truly dark sky, often for the first time, the reaction is telling. Silence, stillness, sometimes disbelief. The sheer number of visible stars can feel overwhelming. This reaction suggests that wonder isn't something we grow out of. It's something that waits, dormant, until given the right conditions to return. Children often experience this most vividly. They ask questions adults struggle to answer. How far away are the stars? Why don't they fall? How many are there? These questions aren't naive. They're fundamental. They arise before formal education, before terminology, before diagrams. They arise because the sky presents a puzzle without instructions. As adults, we sometimes lose the habit of asking questions that don't have immediate practical answers. But the stars tend to bypass that resistance. They invite questions that don't demand resolution. You can wonder without expecting closure. You can ask without planning to solve. That kind of curiosity is rare in daily life, and valuable. There's also the role of shared experience. Every human who has ever lived under an open sky has seen the same general stars, even if their interpretations differed. That creates a quiet continuity across time. When you look up, you're doing something that countless others have done, across thousands of years, without knowing your name or language. Wonder becomes a kind of connection. This connection extends into modern science as well. Astronomers, despite working with complex instruments and abstract data, are often motivated by the same simple impulse. What's out there? How much of it is there? How does it all fit together? The tools are different. The questions are not. When scientists talk about counting stars, they are participating in a long tradition of upward curiosity. They are formalizing a question that predates science itself. The difference is not in motivation, but in method. Instead of myths and stories, they use models and measurements. Instead of naked eyes, they use detectors sensitive to wavelengths invisible to human vision. But the underlying wonder remains. It's also worth noting that wondering about stars is one of the few activities that naturally slows people down. You can't rush the sky. You can't skim it. It doesn't reward urgency. It invites lingering. That makes it especially compatible with rest, reflection, and sleep. The mind shifts from doing to observing, from controlling to noticing. This slowing is important because questions about the universe are not meant to be answered quickly. They unfold over time, both historically and individually. A child's question becomes an adult's curiosity. An amateur's curiosity becomes a researcher's career. Each stage builds on the last without erasing it. So when we ask how many stars are in the universe, we're not just asking for a number. We're continuing a conversation that began the first time someone noticed the sky didn't end at the horizon. We're expressing the same mix of curiosity and humility that has always accompanied that upward glance. At some point, numbers stop behaving the way we expect them to. They still follow the rules of mathematics, of course, but our intuition quietly gives up. We can handle 1, 10, 100, even 1,000 without much trouble. We can picture them. We can feel their difference. But as quantities grow larger, especially when they grow far beyond anything we encounter in daily life, numbers lose their texture. They become symbols rather than experiences. This is where counting the stars truly begins to feel strange. Not because the stars themselves are unusual, but because our minds were never designed to hold that scale comfortably. When we talk about counting something, we usually imagine a process with a clear beginning and end, one object after another, a pile that gets smaller as the count gets larger. Even when we estimate, we still rely on familiar anchors. We count groups, rows, containers. We extrapolate from something we understand to something slightly bigger. But stars refuse to cooperate with this approach almost immediately, not because they are hidden or evasive, but because their sheer number dissolves the very idea of direct counting. To understand why, it helps to think about how humans naturally relate to quantity. Our brains evolved to manage numbers that mattered for survival. How many people are nearby? How many animals are in a herd? How much food is left? These are small, manageable quantities. Even today, studies show that humans are very good at instantly recognizing quantities up to about 4 or 5 without counting. Beyond that, we rely on learned strategies. Grouping, estimating, using symbols. Numbers become abstractions. This shift from perception to abstraction happens quietly, and most of the time we don't notice it. When someone says a city has 1 million residents, we nod, even though we cannot truly imagine 1 million individual lives at once. The number functions as information, not experience. When the number grows to 1 billion, the gap widens further. When it reaches into the trillions, it becomes almost entirely symbolic. It tells us something is very large, but not what that largeness feels like. Stars live permanently in that symbolic territory. Even the most conservative estimates place their numbers far beyond anything we can intuitively grasp. So when scientists talk about counting stars, they are not engaging in counting as we usually understand it. They are doing something closer to statistical storytelling, using small, measurable pieces of information to build a picture of something incomprehensibly vast. This is where the language around stars can become misleading without intending to be. Phrases like, "there are about 10 billion trillion stars" sound precise, but they mask the process behind them. That number does not come from tallying individual points of light. It comes from layers of estimation stacked carefully on top of one another, each layer resting on assumptions, measurements, and models that are constantly refined. One reason numbers begin to feel strange here is that distance interferes with counting. On Earth, counting is limited by time and effort. In space, it is limited by light itself. Stars are not just numerous, they are far away. so far away that many of them appear not as stars at all but as blended light, merged together into a faint glow. Even our most powerful telescopes cannot separate every individual star in distant galaxies. Instead, they collect light from billions of stars at once, compressing unimaginable complexity into a single measurement. When astronomers look at a distant galaxy, they do not see a collection of individual suns, they see brightness. From that brightness, they infer how many stars must be there to produce it. This inference depends on knowing how bright stars typically are, how they are distributed by mass, and how they evolve over time. Already, counting has turned into a layered reasoning process rather than a direct observation. And this is where things start to feel even stranger. Because the stars themselves are not uniform, they vary enormously. Some are small and dim, barely glowing. Others are massive and brilliant, outshining thousands of smaller stars combined. If a galaxy's light is dominated by a few bright stars, the total brightness can be misleading. A galaxy might appear bright without containing as many stars as a dimmer-looking one composed mostly of faint stars. So astronomers must account for stellar populations, not just light output. This leads to another complication. We cannot see all stars equally well, even within our own galaxy. Dust clouds block light. Some stars emit more energy and wavelengths our eyes cannot see. Others are simply too faint. So even locally, counting requires correction. You count what you can see, then estimate what you cannot, based on models of how stars tend to form and distribute themselves. At this point, the idea of a single solid number begins to soften. The answer to how many stars exist is not a fixed value carved into reality. It is a range, a best estimate given current knowledge. As our tools improve, that estimate shifts. This is not a failure of science, it is a feature of it. Large-scale questions are answered progressively, not conclusively. The strangeness of these numbers also comes from how they relate to time. Stars are not static objects. They are born, they change, and they die. The number of stars in the universe is not constant. It has changed over billions of years and continues to change. Some stars collapse into remnants, others merge. New stars form from clouds of gas. So when we ask how many stars there are, we are implicitly asking at what moment. Most estimates refer to the current era of the observable universe. But even that phrase hides complexity. Light from distant galaxies takes billions of years to reach us. When we observe those galaxies, we are seeing them as they were long ago. The stars we count in them may no longer exist in the same form today, so the number of stars we estimate is a mixture of different cosmic times stitched together by the speed of light. This alone makes the idea of a single present-day star count almost poetic, even though we're avoiding poetic language. It is a number assembled from the past using light that has travelled vast distances, carrying information that is always slightly out of date. Counting stars means counting history as much as objects. Another reason numbers begin to feel strange here is comparison. Humans understand numbers best when they can compare them to something familiar. But there is nothing familiar at this scale. Saying there are more stars than grains of sand on Earth is a common comparison, but even that begins to break down under scrutiny. Most people have never seen all the sand on a single beach, let alone every desert and coastline combined. The comparison gestures toward largeness without truly grounding it. Scientists themselves are aware of this limitation. When they discuss star counts, they rarely expect anyone to intuitively grasp the number. The number serves a different purpose. It anchors theories. It constrains models of galaxy formation. It helps test ideas about how matter evolved after the early universe. Its usefulness is internal to science, not dependent on human intuition. Still, there is something quietly unsettling about numbers that escape intuition. They remind us that reality does not scale to our comfort. The universe does not pause at the edge of what we can imagine. It continues outward, indifferent to whether we can picture it. This is part of what makes cosmic numbers both fascinating and exhausting. The mind reaches for a handhold and finds none. To cope with this, astronomers often work in layers. They count stars in a small region where individual stars can be resolved clearly. Then they study how that region compares to others. They identify patterns. For example, they might determine how many stars typically exist per unit of mass in a galaxy, or how star density changes from the center of a galaxy to its edges. These patterns become tools. Instead of counting everything, they count representative samples. This is similar to how one might estimate the number of trees in a forest. You count how many trees are in a small plot, then multiply by the forest's area, adjusting for terrain and density variations. The estimate improves as you refine your sampling, but it never becomes exact in the way counting objects in a room does. And just like forests, galaxies are not uniform. They have dense cores, sparse outskirts, clusters, and voids. As the scale increases further, from galaxies to clusters of galaxies to the observable universe as a whole, estimation becomes even more abstract. Astronomers must estimate not only how many stars are in an average galaxy, but how many galaxies exist, how they are distributed, and how that distribution changes with distance and time. Each step adds uncertainty, but also structure. The uncertainties are not random. They are bounded, constrained by observation. This is why you will often hear star counts described as orders of magnitude rather than precise figures. Saying there are on the order of 10 to the 22nd stars is more honest than pretending to know the exact digit sequence. It acknowledges that the number is enormous and approximate, not exact and final. The strangeness also comes from language itself. Words like million and billion once described quantities that felt unimaginably large. Now they appear casually in discussions of money, data, and population. But even then, stars push beyond these scales into territory where prefixes pile up awkwardly. Trillion, quadrillion, quintillion, sextillion. Each step adds zeros, but subtracts meaning. When numbers lose meaning, the mind often shifts from comprehension to acceptance. You stop trying to picture the quantity and instead focus on relationships. More than, less than, comparable to, greater by many orders of magnitude. This relational understanding is how scientists work comfortably with enormous numbers without becoming overwhelmed by them. It's also how this exploration will continue. Rather than forcing a mental image of every star, we'll focus on how scientists build their estimates, what those estimates depend on, and why they change. We'll move gradually from the familiar to the unfamiliar, letting the scale expand step by step, rather than all at once. Because the strangeness of these numbers is not a barrier. It's an invitation to slow down, to accept that some questions are not meant to be resolved in a single glance. Counting the uncountable is less about arriving at a number, and more about understanding why the number resists us. When the question of how many stars exist begins to feel overwhelming, the most sensible thing to do is stop expanding outward and turn inward instead. Before thinking about the entire universe, it helps to understand the place we already inhabit, our local neighbourhood. The vast system of stars we are embedded within is not a distant object we observe from the outside. It is the environment we live inside of, and that makes it both familiar and strangely difficult to visualize at the same time. The Milky Way is not a backdrop. It is a structure we occupy. Every star you can see with the naked eye belongs to it. Every constellation, no matter how ancient or culturally specific its story might be, is drawn entirely from stars that share our galactic home. Even when you look at the hazy band of light stretching across a dark sky, you're not seeing outward into deep space in a general sense. You're looking sideways through a dense, flattened system of stars, dust, and gas, all bound together by gravity and motion. This alone reshapes how we think about counting stars. When we ask how many stars are in the Milky Way, we're not asking how many objects are scattered across a simple volume. We're asking how many stars are distributed through a rotating, layered, uneven structure that spans tens of thousands of light years and contains regions of wildly different density. Some areas are packed tightly with stars, others are comparatively empty. Some regions are actively forming new stars. Others are quiet, dominated by older populations that have been stable for billions of years. Our position inside this system complicates matters further. We do not have the luxury of stepping back and taking a clean picture of the Milky Way from the outside. All images you have seen of it as a spiral galaxy are reconstructions, built from indirect measurements and comparisons with other galaxies we believe are similar. From our vantage point, large portions of the galaxy are obscured by dust, and our view is limited to what light can reach us without being scattered or absorbed. Despite these limitations, astronomers have learned a great deal about the Milky Way structure. It is a barred spiral galaxy, meaning it has a dense, elongated central region from which spiral arms extend outward. These arms are not rigid structures like spokes on a wheel. They are more like traffic jams in a rotating disk, regions where stars and gas bunch up temporarily as they orbit the galactic center. The stars themselves move in and out of these arms over time. The galaxy is enormous by everyday standards. Its disk spans roughly 100,000 light-years across. To put that into perspective, a light-year is the distance light travels in a year, moving at about 300,000 kilometers per second. Even that comparison doesn't help much intuitively, but it does underscore the scale involved. Our solar system sits roughly halfway between the center of the galaxy and its outer edge, embedded in one of the spiral arms, orbiting the center once every couple 100 million years. Within this vast disk lies most of the Milky Way's stars. Above and below it extends a thinner halo containing older stars and globular clusters, some of which are among the oldest objects in the galaxy. At the very center lies a dense core, crowded with stars and orbiting a supermassive black hole. Each of these regions contributes differently to the overall star count. So how do scientists begin to estimate how many stars this system contains? They start locally. In regions close enough for individual stars to be resolved clearly, astronomers can count stars directly. They can measure how many stars exist within a certain volume of space near the Sun, classify them by type and brightness, and determine how common different kinds of stars are. This local census becomes a baseline. From there, they examine how star density changes with distance from the galactic center. Observations show that stars are more densely packed toward the center and more spread out toward the edges. The disk itself has a thickness that varies with radius, and the halo contributes a smaller but significant number of stars that orbit in more elongated paths. Infrared observations play a crucial role here. Much of the Milky Way is obscured by dust that blocks visible light. Infrared light, however, passes through dust more easily, revealing stars that would otherwise be hidden. Space-based observatories have mapped large portions of the galaxy in infrared, providing a much clearer picture of how stars are distributed throughout the disk and central regions. Even with these tools, counting remains indirect. Astronomers measure brightness and infer numbers. They count stars in representative slices and extrapolate outward. They compare the Milky Way to other spiral galaxies whose total light and mass can be estimated more easily from an external viewpoint. All of these methods converge on a broad range rather than a precise figure. The commonly cited estimate is that the Milky Way contains somewhere between 100 billion and 400 billion stars. That range alone tells an important story. The uncertainty is not trivial. It reflects real gaps in knowledge, particularly about faint, low-mass stars that are difficult to detect but may be extremely numerous. Small, dim stars known as red dwarfs contribute very little light individually, but they are thought to make up the majority of stars in the galaxy. If they are more common than current models suggest, the total star count shifts upward. If less common, it shifts downward. There are also stellar remnants to consider. White dwarfs, neutron stars, and black holes are the end states of stellar evolution. They no longer shine like ordinary stars, but they are still stars in a meaningful sense. Counting them requires additional modelling, since many are invisible except through their gravitational effects or rare interactions with nearby matter. Another factor is star formation history. The Milky Way did not form all its stars at once. It has been forming stars continuously for over 13 billion years, though not at a constant rate. Periods of intense star formation alternated with quieter eras. Mergers with smaller galaxies added stars that formed elsewhere. All of this affects the current population. This layered history means that the Milky Way is not a static container of stars, it is an evolving system. Some stars are born as others die. The total number changes slowly over time. When we talk about the current number of stars, we are freezing a dynamic process into a snapshot. Understanding this helps explain why counting stars feels different from counting anything else. You're not just tallying objects, you're summarizing a long, ongoing process. Each star represents a unique history, a balance between gravity and nuclear fusion, a lifespan that may span millions or billions of years. When you multiply that by hundreds of billions, the mind naturally resists holding it all at once. Still, there is something grounding about starting here. The Milky Way may be vast, but it is not abstract. It is the reason the night sky looks the way it does. It is why the sky appears brighter in some directions than others. It is why the band of light arches overhead on clear nights. These are not random features. They are the visible texture of our local stellar environment. When you consider that every visible star belongs to this one galaxy, the scale becomes both smaller and larger at the same time. Smaller because what you see is part of a single structure rather than the entire universe. Larger because even that single structure contains more stars than there are humans who have ever lived. This local focus also sets an important baseline for what comes next. Once you understand that our home galaxy alone holds hundreds of billions of stars, the leap to thinking about other galaxies becomes more manageable. You're no longer multiplying from one to many blindly. You're multiplying something you've already spent time with, something that now has shape, structure, and internal logic. Hundreds of billions of stars, all gravitationally bound, all moving together through space, forming the luminous framework of our night sky. Not infinite, not uncountable in principle, but vast enough that even our best estimates carry uncertainty. A local neighbourhood by cosmic standards, yet already far beyond everyday experience. Living inside a spiral galaxy is a peculiar situation. It's like trying to understand the shape of a city while standing in the middle of one street, surrounded by buildings, traffic, and noise. You can see what's nearby clearly enough, but the overall structure remains hidden unless you gather clues slowly, patiently, and indirectly. That is exactly the challenge astronomers face when they try to understand the Milky Way. We don't observe it as a complete object hanging in space. We experience it from within, immersed in its disk, moving along with its rotation, surrounded by its stars, gas, and dust. Everything we know about its shape, its scale, and its population has been pieced together from this internal vantage point. The Milky Way is called a spiral galaxy because of the broad pattern its stars follow, but that word can be misleading if taken too literally. From the inside, there are no neat arms curving gracefully across the sky. Instead, there are subtle gradients of brightness, patches of obscuring dust, clusters of stars here and there, and a general sense that some directions are more crowded than others. The spiral structure is something inferred rather than directly seen, reconstructed from measurements of motion, distribution, and comparison. One of the first things to understand about the galaxy we live in is that it is not flat in the simple sense. It has a disk, yes, but that disk has thickness. Stars are distributed above and below a central plane, with younger stars and gas tending to stay closer to it, while older stars wander farther away over time. This creates layers, like a slowly stirred liquid where heavier components settle differently than lighter ones. From our position within one of these layers, the galaxy feels more like an environment than a shape. Our Sun is embedded in this disk, orbiting the galactic centre along with billions of other stars. This orbit is not fast by human standards. It takes the Sun roughly 200 to 250 million years to complete a single circuit. During that time, Entire species can rise and fall on Earth. Continents can shift. Climate patterns can change. The galaxy, by contrast, barely notices. Its rotation is steady, massive, and patient. This motion matters for understanding the spiral structure. The arms are not rigid collections of the same stars moving together forever. Instead, they are regions where stars and gas are more densely packed at any given time. As material orbits the center, it flows into these regions, lingers for a while, and then moves on. New stars often form there because the higher density of gas encourages collapse. That's why spiral arms tend to glow with young, bright stars. Older stars, meanwhile, drift away, populating the space between arms. From inside the disk, this creates a sky that is uneven in subtle ways. Some directions contain more stars. Some regions appear brighter or clouded. The familiar band of the Milky Way stretching across the night sky is the most obvious manifestation of this structure. When you look along the plane of the disk, your line of sight passes through enormous numbers of stars overlapping and blending together. When you look away from it, you are peering out of the disk into regions where stars are sparser and the sky appears darker. Understanding this geometry was not straightforward. Early astronomers assumed the Sun might sit near the centre of the galaxy, simply because that felt intuitively reasonable. Over time, as distances to stars were measured more accurately, it became clear that we're not centrally located at all. The density of stars increases dramatically in one direction, indicating the true centre lies far from us. This realization was a humbling one, reinforcing a pattern that repeats throughout astronomy. We are not where we once assumed we were. At the heart of the Milky Way lies a dense region packed with stars, gas, and dust, orbiting a supermassive black hole. This central area is difficult to observe directly in visible light because intervening dust blocks much of it. Infrared and radio observations have been essential in revealing what's there. These wavelengths pass through dust more easily, allowing astronomers to map stellar motions and infer mass distributions. The presence of a supermassive black hole at the centre is not unusual. Most large galaxies appear to host one. In the Milky Way, it has a mass millions of times that of the Sun. Despite its size, it does not dominate the galaxy in the dramatic way popular culture sometimes suggests. Stars orbit it as part of the overall galactic system, influenced far more by the combined mass of all the surrounding stars than by the black hole alone. Moving outward from the centre, the disk dominates. This is where most stars reside. But even within the disk, conditions vary. Some regions are rich in gas and actively forming stars. Others are comparatively quiet, populated by older stars that formed long ago. The distribution of star types changes with distance from the centre, reflecting differences in chemical composition and formation history. Then there is the halo, a roughly spherical region extending far beyond the disk. It contains relatively few stars compared to the disk, but those it does contain are among the oldest in the galaxy. Many reside in globular clusters, tightly bound groups of stars that orbit the galactic centre in paths that can be highly inclined relative to the disk. These clusters provide important clues about the early stages of galaxy formation, when the Milky Way was assembling from smaller components. From the inside, the halo is almost invisible. Its stars are spread thinly across the sky, easily overlooked, yet it extends far beyond the luminous disk, increasing the galaxy's true size significantly. Understanding its contribution is another reason counting stars is so complex. Even when regions contribute only a small fraction of the total light, they may still contain substantial numbers of stars. The Milky Way did not form in isolation. Over billions of years it has interacted with and absorbed smaller galaxies. Some of their stars were assimilated into the disk, others were scattered into the halo. Streams of stars moving together through space betrayed these ancient mergers. They are like fossil records written in motion rather than stone. Each stream represents a population of stars that formed together elsewhere, and now share a common path through our galaxy. All of this history is encoded in the current distribution of stars. When astronomers attempt to count them, they are reading that history indirectly. Variations in density, composition and motion all inform models of how many stars must be present to produce what we observe. It is a process that relies on patterns rather than inventories. Another complicating factor is dust. Interstellar dust is not evenly distributed. It clumps into clouds that can obscure entire regions of the galaxy from view in visible light. These clouds are especially prevalent in the disk, where star formation occurs. They hide stars behind them, skewing counts unless corrections are applied. Infrared surveys help, but even they have limits. Then there is the question of faint stars. The majority of stars in the Milky Way are small and dim. They burn their fuel slowly, shining weakly for trillions of years. Individually, they are difficult to detect beyond relatively nearby distances. Collectively, they may dominate the star count. Estimating their numbers requires assumptions about how common they are relative to brighter stars, assumptions informed by local observations and theoretical models. From inside the galaxy, astronomers must constantly ask whether what they see nearby is representative of what exists elsewhere. Is the stellar neighbourhood around the Sun typical, or is it unusual in some way? Does the proportion of faint to bright stars change with location? Does star formation proceed differently closer to the centre than farther out? Each of these questions affects the final count. Despite all this uncertainty, the internal view has advantages. Being embedded within the galaxy allows for extremely detailed study of individual stars, star clusters, and stellar motions. Precise measurements of distances and velocities help refine models of galactic structure. Over time, these local details add up to a coherent global picture. There is also something quietly profound about studying the galaxy from within. We are not external observers detached from the system. Our planet, our sun, and even our bodies are products of this galaxy's history. The elements heavier than hydrogen and helium were forged in earlier generations of stars that lived and died long before the sun formed. When we count stars, we are, in a sense, counting ancestors. This perspective changes the emotional tone of the numbers. The Milky Way is not just a container of hundreds of billions of stars, it is a dynamic, evolving system that has shaped the conditions for life here. Understanding it from the inside is not just a technical challenge. It is a way of understanding context. As we sit quietly under the night sky, the spiral structure is not obvious. What we see are individual points of light, patterns handed down through culture, and a faint glow stretching across darkness. Yet behind that familiar view lies a vast rotating system, layered, complex, and only partially revealed to us. Each improvement in observation peels back another layer, never fully exposing the whole, but making it clearer nonetheless. It's enough to sit with the idea that we live inside a spiral of stars moving along with it, seeing it from within rather than above. A structure so large that its full shape can only be inferred, yet so intimate that it fills our night sky. For a very long time, the Milky Way was thought to be everything. Not metaphorically, not poetically, but literally. The entire universe, as far as anyone could tell, consisted of the stars visible in the night sky and the faint cloudy patches that drifted among them. Those patches were mysterious, yes, but they were assumed to belong to the same overall structure. From the inside, it made sense. When you live within something vast, it's easy to mistake the boundary of your perception for the boundary of reality itself. This assumption held for centuries, not because people lacked imagination, but because they lacked evidence. The sky, even through early telescopes, appeared finite in a comforting way. Stars were points. Nebulous smears were curiosities. Everything seemed part of one grand but singular system. The idea that there might be entire other systems, each filled with stars, lying far beyond our own, simply didn't have solid footing yet. It was speculation without anchors. What changed was not a single discovery, but a slow accumulation of unease. As telescopes improved, those faint smudges refused to resolve themselves into ordinary stars. Some appeared spiral-shaped. Others were elongated or irregular. They behaved differently than expected if they were merely clouds of gas within the Milky Way. Still, the distances involved were so uncertain that debates dragged on for decades. Were these objects nearby, or impossibly far away? Were they part of our galaxy, or something else entirely? The question was not trivial, because its answer carried enormous consequences. If those objects were distant star systems, then the universe was far larger than anyone had dared to confirm. The Milky Way would no longer be the universe. It would be one example among many. And suddenly, counting stars would not stop at the edges of our galaxy. It would explode outward. When the evidence finally settled, it did so decisively. Measurements of distance showed that these spiral nebulae were far too distant to belong to the Milky Way. They were galaxies in their own right, each containing vast numbers of stars. This realization did not arrive with fanfare in everyday life, but in science it was seismic. The universe did not gently expand, it multiplied. From that moment on, the night sky changed, even though it looked the same. Every faint patch of light became a potential city of stars. Every dark region between visible stars became less empty than it appeared. The universe transformed from a single structure into a population. Understanding other galaxies presented a new challenge. Unlike the Milky Way, which we experience from within, other galaxies are external objects. We can see their shapes more clearly, but we cannot resolve most of their individual stars unless they are very close. This creates an inversion of perspective. For our own galaxy, we know individual stars well but struggle with the overall shape. For distant galaxies, we see the shape but not the details. This external view is both a gift and a limitation. From far away, galaxies reveal their structure honestly. Spirals, ellipticals, irregular forms, dense cores, extended halos. From this, astronomers can classify galaxies, compare them, and identify patterns. They can estimate total mass, total brightness, and overall star formation activity. But they must infer the star count indirectly, just as they do for distant regions of the Milky Way, only now at an even grander scale. One of the first surprises was variety. Galaxies are not all like the Milky Way. Some are much smaller, containing only a few billion stars. Others are enormous, with trillions. Some are neat and symmetrical. Others are distorted, stretched by gravitational interactions or shaped by violent pasts. This diversity matters deeply when estimating how many stars exist overall, because it means there is no single, average galaxy that can be multiplied safely without context. There are dwarf galaxies, for example, faint and low in mass, often orbiting larger galaxies like satellites. Individually, they don't contribute many stars compared to giants, but they are numerous. Then there are massive elliptical galaxies, often found in dense clusters, containing old stars and vast stellar populations. A single one of these can rival or exceed the Milky Way's star count by a large margin. Between these extremes lie countless intermediate forms, spiral galaxies similar to ours, irregular galaxies still forming stars chaotically, galaxies caught in the act of merging, their stars flung into long tidal streams. Each type contributes differently to the cosmic total. Discovering other galaxies also revealed something else quietly unsettling. Space between galaxies is not empty in the way we once imagined. Galaxies are grouped into clusters, and clusters into superclusters, forming a vast cosmic web. Stars, of course, remain bound to galaxies, but galaxies themselves are not scattered randomly. They trace filaments of matter stretching across unimaginable distances. This structure influences how many galaxies exist in different regions of the universe, and therefore how many stars. When astronomers attempt to estimate the total number of stars beyond the Milky Way, they must first estimate how many galaxies exist. This alone is a moving target. Early estimates placed the number in the billions. Improved observations pushed it higher. Deep field images staring at seemingly empty patches of sky for weeks at a time revealed thousands of galaxies where none had been seen before. Each new survey added layers. But even the deepest observations have limits. There are galaxies too faint, too small, or too distant to be detected with current instruments. Some formed early and faded. Others never accumulated enough mass to shine brightly. Their stars exist, but their collective light is subtle. So when scientists talk about the number of galaxies in the observable universe, they speak in ranges rather than absolutes. This uncertainty compounds when translating galaxies into stars. You cannot simply multiply the number of galaxies by the number of stars in the Milky Way and call it done. Galaxies vary too widely. Instead, astronomers categorize galaxies by type, estimate typical star counts for each category, and then estimate how many galaxies of each type exist. It's a statistical approach layered on top of another statistical approach. What makes this process trustworthy is not precision, but consistency. Independent methods tend to converge on similar ranges: brightness distributions, mass measurements, simulations of galaxy formation. Each line of evidence constrains the others. When the numbers align within a certain range, confidence grows, even if exactness remains elusive. Another subtle complication comes from cosmic time. Galaxies evolve, star formation rates change. The universe was once much more active in forming stars than it is now. When we observe distant galaxies, we are seeing them as they were billions of years ago, often during periods of intense star formation. This means that the number of stars per galaxy was changing rapidly at that time. So when we count stars across the observable universe, we are summing populations from different eras. Some galaxies we see had not yet formed many of the stars they will eventually contain. Others may have already lost stars through interactions or internal processes. The total number is a snapshot stitched together from different moments in cosmic history. This temporal layering makes the question richer, but also stranger. The universe does not present itself at a single moment. Light carries information forward, but time remains embedded in what we see. Counting stars means counting across time as well as space. There is also the matter of perspective. From Earth, distant galaxies appear small and faint. Their light blends together, but if you could stand within one of them, surrounded by its stars, it would feel just as vast and complex as the Milky Way does to us. Each galaxy is a local universe to itself, with its own structure, history, and stellar population. Realizing this shifts how we think about scale. The universe is not just large, it is repetitively large. This repetition has a calming quality when approached slowly. The same processes that shaped our galaxy operate elsewhere. Gravity gathers matter, gas collapses, stars ignite, some burn fast and die young, others persist quietly for trillions of years. The details vary, but the pattern repeats. When counting stars beyond home, we're counting the repetition of familiar physics across enormous distances. As more galaxies were discovered, the night sky quietly transformed again. What once seemed like a dome with a few thousand points of light became a window onto a universe filled with islands of stars, each separated by vast stretches of space. The darkness between visible stars became less empty, not because it was filled with stars, but because it was filled with potential, with structures too distant to resolve individually. This realization deepened the original question rather than answering it. How many stars are there really? Now includes not just what exists, but what we can see, what we can infer, and what remains hidden beyond current limits. It becomes a question about observation as much as existence. Still, discovering other galaxies provided something invaluable. It gave us context. The Milky Way is no longer an isolated marvel. It is one participant in a much larger ensemble. Its star count, once astonishing, becomes a unit of comparison rather than an endpoint, As we continue outward from home, this shift in perspective will matter. The universe grows not in a smooth gradient, but in steps. First a solar system, then a galaxy, then many galaxies. Each step multiplies scale and complexity, and with each step counting becomes less about enumeration and more about understanding distributions. The Milky Way gave us a sense of local abundance. Other galaxies show us that abundance is not unique. It is common, widespread, structured, and yet still bounded by the same physical laws. At first glance, galaxies do not announce themselves as the grand structures we now know them to be. Through early telescopes, and even through modern ones when pushed to their limits, they often appear as faint smudges, barely distinct from the darkness around them. They don't look like collections of stars. They look like mistakes, like dust on a lens, like something half seen that might disappear if you blink. And yet, hidden inside each of those smudges is an entire system, vast beyond everyday comprehension, containing stars by the billions or trillions. Understanding how those smudges multiply into cities of light is a story about patience, technology, and a gradual reshaping of what we mean by many. When astronomers first realized that galaxies existed beyond the Milky Way, the revelation was staggering, but it still felt manageable. There were other galaxies, yes, but how many could there really be? A few hundred? A few thousand? Even tens of thousands sounded enormous by the standards of the time. The night sky, after all, looked finite. It had edges defined by darkness. It did not obviously suggest an endless population of star systems. The problem was not imagination, it was access. Early observations were limited by sensitivity. Telescopes could only collect so much light, and faint objects simply slipped beneath the threshold of detection. If a galaxy was too distant, too small, or too spread out, it might as well not exist as far as the instruments were concerned. So the early universe of galaxies was sparse by necessity, not by truth. As technology improved, the sky began to change again, not in appearance to the naked eye, but in the data astronomers collected. Longer exposures revealed more objects. Better detectors captured fainter light. Observations at different wavelengths uncovered structures invisible in ordinary optical light. Each improvement did something subtle, but profound. It didn't just sharpen what was already known. It revealed that what was known was incomplete. This became especially clear when astronomers began to stare deeply into small patches of sky. Instead of surveying wide areas shallowly, they focused all their attention on tiny regions, collecting light over days or weeks. What emerged from these deep observations was astonishing. Areas of sky that had once appeared empty suddenly filled with galaxies. Not stars, but galaxies. Thousands of them, packed into a region no larger than a grain of sand held at arm's length. These images changed the conversation. The universe was not lightly sprinkled with galaxies. It was crowded with them. The darkness between nearby stars was not empty at all. It was simply filled with objects too distant and faint to be noticed casually. But even this was not the end of the multiplication. Each galaxy seen in a deep field was itself only the visible tip of a much larger population. For every bright galaxy detected, there were others just below the detection threshold. Smaller, dimmer, more diffuse. Their stars contributed light, but not enough to stand out individually. They blended into the background, forming a faint glow that hinted at even greater numbers. This is where galaxies truly begin to multiply in a way that feels almost abstract. The count no longer increases linearly with better instruments, it accelerates. Each gain in sensitivity reveals disproportionately more objects. This happens because the universe contains many more small and faint galaxies than large, bright ones. Bright galaxies are rare, faint ones are common. When your instruments improve just enough to detect the next tier of faintness, the population explodes. This pattern is familiar in other contexts. In a city, there are fewer skyscrapers than houses, fewer houses than apartments, fewer apartments than individual rooms. As you lower the threshold of what you count, numbers increase rapidly. The same principle applies to galaxies. The universe favours the small and numerous. Understanding this distribution is crucial for estimating how many galaxies exist overall. Astronomers don't simply count what they can see and assume that's all there is. They analyse how galaxy brightness is distributed, then extrapolate downward to estimate how many faint galaxies remain unseen. This requires assumptions, but those assumptions are constrained by physics and observation. You can't invent galaxies arbitrarily. Their formation depends on dark matter, gas availability, and cosmic history. Over time, this approach has led to a dramatic revision of galaxy counts. What was once thought to be a universe with a few billion galaxies became a universe with hundreds of billions, and then possibly trillions. Each revision wasn't a correction of a small error. It was a recognition that previous views were sampling only the brightest layer of a much deeper population. This multiplication matters because each galaxy brings its own stars with it. When galaxies multiply, stars multiply with them. But the relationship is not straightforward. Smaller galaxies tend to have fewer stars. Some dwarf galaxies contain only a few million stars, a tiny fraction of the Milky Way's population. Others have even fewer. Yet their sheer numbers mean they contribute significantly to the overall count. There is also the question of galaxy evolution. Many small galaxies formed early in the universe's history, and were later absorbed by larger ones. Their stars did not vanish. They were redistributed. Some joined galactic disks. Others became part of halos or stellar streams. When counting stars today, these merged populations are already included within larger galaxies. But when counting galaxies across cosmic time, those smaller systems still matter, because they existed as independent units for long periods. This introduces a subtle distinction. Are we counting galaxies as they exist now, or as they have existed across time? Most estimates focus on the present observable universe, counting galaxies that can be identified as distinct systems today. But the historical abundance of galaxies was likely even higher. Many have merged, faded, or been disrupted beyond easy recognition. Even within the present universe, defining what counts as a galaxy is not always simple. At the smallest scales, the distinction between a large star cluster and a small galaxy can blur. Some systems contain dark matter halos and behave like galaxies, despite having very few stars. Others sit at the edge of detectability, challenging classification. Whether these borderline objects are included affects counts, sometimes significantly. As galaxies multiply in number, they also multiply in arrangement. They do not exist in isolation. They cluster together under gravity, forming groups, clusters, and larger structures. In dense regions, interactions are common. Galaxies collide, merge, and distort each other. These interactions can trigger bursts of star formation, temporarily increasing the number of luminous stars. Over time, they also reduce the number of distinct galaxies by combining them into larger systems. So the population of galaxies is not static. It grows through formation and shrinks through merging. The balance between these processes has shifted over cosmic history. Early on, formation dominated. Later, merging became more common. Today, both processes continue, but at a slower pace than during the universe's more active youth. This dynamism complicates the idea of a simple galaxy count. When astronomers estimate how many galaxies exist, they are capturing a moment in a long evolutionary process. The number is meaningful, but not eternal. It changes, slowly but inexorably, as structures continue to evolve. Still, even with all this complexity, one fact remains clear. Galaxies are not rare. They are the fundamental units of the visible universe. Wherever matter was dense enough to collapse under gravity, galaxies formed. Wherever galaxies formed, stars followed. The multiplication of galaxies is the multiplication of star-forming environments. This realization shifts how we think about the night sky. The visible stars are not representative of the universe's richness. They are a local sampling. The true abundance lies far beyond what the eye can see, in structures so distant that their combined light barely reaches us. When astronomers speak of galaxies as cities of light, the phrase is not metaphorical in a casual sense. Cities are concentrations of activity, density, and interaction. They are places where individual lives become part of a larger system. Galaxies function similarly. Stars form, evolve, and die within them, influenced by their surroundings. The city analogy works not because galaxies are orderly, but because they are complex, layered, and internally structured. And like cities, galaxies vary widely. Some are quiet, with little new activity. Others are bustling with star formation. Some are ancient and settled. Others are chaotic, shaped by recent encounters. Counting them means acknowledging this diversity rather than flattening it into a single average. As galaxies multiply, the numbers involved become less about totals and more about distributions. How many large galaxies exist versus small ones? How star-rich are different types? How environment influences star formation? These questions feed directly into estimates of total star counts. What emerges from this slow accumulation of data is not a neat answer, but a robust picture. The universe contains an enormous number of galaxies, far more than intuition would suggest. Each contains stars. Some contain vast numbers, others contribute modestly. Together, they form a population so large that even the act of estimating it pushes the limits of current understanding. And yet this multiplication does not make the universe feel chaotic. On the contrary, patterns emerge. Regularities appear. The same physical laws operate everywhere. The same processes repeat at different scales. This consistency allows astronomers to extend what they learn locally to the farthest reaches they can observe. Counting stars across the universe is inseparable from understanding how galaxies multiply, evolve, and distribute themselves across space and time. The smudges that once puzzled early observers are now recognized as the basic building blocks of cosmic abundance. There is a quiet assumption built into most conversations about the universe, one that rarely gets stated outright. We tend to imagine that what we can see is roughly what exists, perhaps with a little extra beyond the edges. But when it comes to deep space, that assumption fails almost immediately. The reach of our telescopes is not a simple extension of eyesight. It is a boundary defined by physics, time, and the finite speed at which information travels. Understanding how far our telescopes can really see means understanding not just distance, but history, limitation, and the way observation itself reshapes the questions we ask. When you look at a distant object on Earth, the delay between the object and your perception of it is negligible. Light takes a fraction of a second to travel from a tree across the field to your eyes. Even the moon, distant as it feels, is seen as it was just over a second ago. These delays are so small they don't register in daily life. Space, however, operates on a completely different scale. There, distance and time are inseparable. To look farther is not just to look deeper into space, but deeper into the past. This simple fact changes everything about how we count stars and galaxies. A telescope does not show us the universe as it is right now. It shows us the universe as it was when the light began its journey toward us. For nearby stars, that journey might take years or decades. For distant galaxies, it can take billions of years. When astronomers push their instruments to the limit, they are not just looking across vast distances, they are looking back toward the earliest eras of cosmic history. This is what people mean when they talk about deep time and deep space as intertwined concepts. You cannot separate them. Every increase in distance is also an increase in look-back time. The farther a galaxy is, the younger the universe was when its light was emitted. This means that the most distant objects we observe are not just far away. They belong to a universe that was fundamentally different from the one we inhabit now. Telescopes, then, are not windows onto a static cosmos. They are archaeological tools, collecting fragments of ancient light and using them to reconstruct a story that spans billions of years. But like all archaeological tools, they have limits. Some regions are beyond reach, not because they do not exist, but because their light has not had enough time to arrive. The finite speed of light sets a hard boundary on observation. The universe is about 13.8 billion years old. That means we cannot see objects whose light has been travelling for longer than that. This boundary defines what is called the observable universe. It is not the entire universe. It is the portion from which light has been able to reach us since cosmic expansion began. Even within this observable region, telescopes face challenges. Light does not travel through empty space unimpeded. It stretches as the universe expands. This stretching shifts light toward longer wavelengths, a phenomenon known as redshift. The farther light travels, the more it is stretched. For very distant galaxies, light that began as visible or ultraviolet arrives as infrared or even radio waves. If your telescope cannot detect those wavelengths, the galaxy remains invisible no matter how long you stare. This is why different telescopes see different universes. Optical telescopes show one version of the cosmos dominated by stars and nearby galaxies. Infrared telescopes reveal another, peering through dust and detecting ancient redshifted light. Radio telescopes uncover structures that shine not through starlight, but through energetic processes and cold gas. No single instrument shows everything. Each one samples a slice of reality defined by wavelength sensitivity. As astronomers built better telescopes, they discovered that depth matters more than width. A shallow survey covering a large area of sky reveals many nearby objects but misses faint distant ones. A deep survey focused on a tiny patch of sky can reveal thousands of distant galaxies packed into a space that once appeared empty. This trade-off between area and depth is fundamental. You can look wide or you can look far. Doing both simultaneously is extraordinarily difficult. The deepest observations ever made illustrate this clearly. When telescopes were pointed at seemingly blank regions of sky and allowed to collect light for extended periods, the result was not darkness, but abundance. Galaxies emerged at every depth, layered by distance and time. Each faint point represented not a star, but a galaxy whose light had been travelling for billions of years. But even these deepest images have edges. There comes a point where galaxies become too faint, too small, or too redshifted to detect with current technology. Their light blends into background noise. Distinguishing signal from randomness becomes a statistical challenge. Beyond that point, galaxies may exist in vast numbers, but they are effectively invisible to us for now. This invisibility does not mean absence, it means limitation. Telescopes are constrained not just by size and sensitivity, but by fundamental cosmic conditions. Early in the universe's history, before stars and galaxies formed, space was filled with opaque plasma that scattered light. There is a literal fog beyond which we cannot see using light alone. This boundary marks the earliest moment from which light can travel freely. Anything earlier is hidden from direct observation. So when we ask how far our telescopes can really see, the answer is layered. They can see to the edge of the observable universe, but only in certain wavelengths. They can see back to the era when the first galaxies formed, but not before. They can detect populations of stars and galaxies indirectly, but not resolve them individually. Each statement is true in its own context. This has important consequences for counting stars. The farther we look, the younger the galaxies we see. Younger galaxies often contain fewer stars because they have not had as much time to form them. Star formation rates were higher in the early universe, but the total accumulated number of stars was lower. This means that distant galaxies contribute differently to star counts than nearby ones. It also means that our view of the universe is incomplete in a specific way. We are better at seeing large, bright galaxies than small, faint ones, especially at great distances. This bias skews raw counts unless corrected. Astronomers must account for what they cannot see by modelling how galaxy populations evolve over time and how many faint systems are likely missing from observations. These corrections rely on a deep understanding of physics, but they also rely on humility. There is always uncertainty at the edge of observation. No matter how advanced a telescope becomes, there will always be objects just beyond its reach. The goal is not to eliminate uncertainty, but to constrain it, to narrow the range of possibilities until meaningful conclusions can be drawn. Another subtle limitation is cosmic variance. The universe is not perfectly uniform at small scales. Some regions contain more galaxies than others. When astronomers observe a small patch of sky deeply, they may be sampling an unusually dense or sparse region. Extrapolating from that region to the entire universe requires caution. Multiple deep fields in different directions help mitigate this, but variation remains. All of this means that telescope reach is not a single number or distance. It is a layered capability defined by wavelength, sensitivity, exposure time, and cosmic conditions. When someone says a telescope can see X billion light years, they're compressing a complex set of conditions into a simplified statement. The reality is more nuanced. What makes this especially relevant to our broader question is that every limit in observation translates into a limit in counting. We can only count what we can detect directly or infer reliably. Beyond that, we rely on models. These models are not guesses pulled from thin air. They're grounded in observed trends, physical laws, and simulations that reproduce what we see locally and extend it outward. Still, there is a philosophical shift that happens here. Counting stars is no longer about discovering an exact total hidden somewhere in the universe. It becomes about understanding distributions within known limits and estimating contributions beyond them. The number becomes less like an inventory and more like a probabilistic statement about abundance. This shift does not weaken the question, it deepens it. It forces us to confront the fact that the universe is larger than our access to it. Our telescopes are powerful, but they are not omniscient. They reveal enough to show us how much remains unseen. There is something quietly fitting about this. The universe reveals itself gradually, never all at once. Each generation of instruments pushes the boundary a little farther, not to reach a final edge, but to expand the region of the known. Each expansion brings with it new galaxies, new stars, and new questions about how representative our view really is. As we stand at the current limits of observation, we're aware that beyond the faintest galaxies, we can detect lies more structure, more stars, and more history than we can yet access. The darkness at the edge of deep images is not emptiness. It is distance combined with time and limitation. If our telescopes cannot see everything directly, how do scientists estimate what lies beyond? How do they turn incomplete observation into meaningful numbers? How do they count stars in regions they cannot fully observe? When you step outside at night and look up, it feels immediate. The stars seem present, active, current, as though they are shining for you in that moment. The light reaches your eyes, your brain registers it, and the experience feels firmly rooted in the present. But that feeling is misleading in a quiet, fundamental way. The night sky is not a view of what is happening now. It is a layered record of what has already happened, stretched across time and distance, delivered to you piece by piece at the speed of light. This is one of the most important ideas to settle into when thinking about stars on a universal scale. Light is not instantaneous. It moves fast, unimaginably fast by human standards, but it still takes time to travel, and in space where distances are vast beyond everyday intuition, that travel time becomes enormous. Every star you see is seen as it was, not as it is. The night sky is a collection of delayed messages, each one carrying information from a different moment in cosmic history. For nearby stars, this delay is small enough to feel negligible. The light from the sun reaches Earth in a little over 8 minutes. When you see sunlight, you're seeing the sun as it was 8 minutes ago. That fact is interesting, but it doesn't feel destabilizing. 8 minutes fits comfortably inside human experience. Even the nearest stars beyond the sun are only a few years away in light travel time. When you look at them, you're seeing something that happened within your lifetime, or at least within a human lifespan. But as your gaze moves farther outward, the delays accumulate quickly. Stars thousands of light years away are seen as they were thousands of years ago. Some of the light entering your eyes tonight began its journey before recorded history, before cities, before agriculture. It has crossed space quietly, uninterrupted, until it happened to intersect with your line of sight at this moment. That alone is a strange thought, but it becomes even stranger as distance increases. When you look at distant galaxies, you're not just seeing the past in a casual sense. You are seeing deep cosmic time. Millions, hundreds of millions, billions of years. The farther away a galaxy is, the younger the universe was when its light began travelling. The stars you see in those galaxies may have changed dramatically since then. Some may have died, others may not even exist anymore. Some galaxies may have merged into larger systems. Others may have been torn apart. The light doesn't update itself. It carries a snapshot forward, frozen at the moment it left. This means that the universe, as we observe it, is not a single coherent moment. It is a collage of different eras. Nearby objects are seen relatively recently. Distant objects are seen as they were long ago. The sky is not synchronized. Time is unevenly distributed across it, and yet we experience it as a single scene. This has profound implications for counting stars. When scientists estimate how many stars exist, they are not counting a universe at one instant. They are counting stars from many different cosmic ages simultaneously. A galaxy seen 10 billion light years away contributes stars that existed 10 billion years ago. A nearby galaxy contributes stars from a much more recent time. These populations are added together, even though they never coexisted in the same moment. That might sound like a problem, but it isn't a flaw. It's an unavoidable consequence of observation. The universe does not present itself as a single frame. It presents itself as a time-extended structure. Any attempt to describe it must accept that. This time layering also explains why the distant universe looks different from the nearby one. When astronomers peer far enough into space, they don't just see fewer galaxies or fainter ones. They see galaxies that look younger, less settled, more chaotic. Their shapes are irregular. Their star formation rates are higher. Their structures are still forming. This is not because distant regions are fundamentally different. It is because we are seeing them earlier in their development. In the early universe, stars were forming at a furious pace. Gas was more abundant. Galaxies were assembling rapidly. Massive stars were more common. Over time, star formation slowed. Gas was consumed or expelled. Galaxies matured. The universe aged. So when we count stars across deep time, we are summing contributions from eras with very different conditions. This raises an important question. When someone asks how many stars are in the universe, do they mean how many stars exist right now, everywhere, simultaneously? Or do they mean how many stars are contained within the observable universe as seen from Earth, across all the times we can observe? These are not the same question, and yet the latter is usually what we answer, because the former is inaccessible. We cannot see the universe as it is now everywhere. There is no universal now that we can access. Relativity itself tells us that simultaneity is not absolute. Different observers moving differently can disagree about what events are happening at the same time. On cosmic scales, this becomes more than a philosophical curiosity. It becomes a practical limitation. So astronomers work with what they can observe. They count stars in galaxies at various distances, model how star formation has changed over time, and use those models to estimate the total number of stars that exist within the observable universe's light cone. It is a carefully defined quantity, even if it is not always described that way in casual conversation. Another subtlety arises when considering how stars age. Stars are not permanent fixtures. They are born from collapsing clouds of gas. They shine for millions to trillions of years depending on their mass, and they eventually exhaust their fuel. Some explode, some collapse, some fade quietly. Over the lifetime of the universe, many generations of stars have existed and disappeared. When we look at the night sky, we are seeing stars at different stages of these life cycles. Some are young and hot, others are old and cool, some are nearing the end of their lives, some may already be gone by now, even though their light is still arriving. The sky is filled with stars that no longer exist in the same form, their presence preserved only in light. This complicates the idea of a star count even further. Are we counting stars that have ever existed? Or stars that exist now? Or stars whose light is currently reaching us? These are three different quantities. The first is vastly larger than the second. The second is inaccessible to direct observation. The third is what we can actually measure. Most scientific estimates focus on the third category because it is observable, but it is important to understand what that means. It means the number is a function of light travel time, cosmic expansion, and star formation history. It is not a timeless census. Cosmic expansion adds another layer of complexity. As the universe expands, distances between galaxies increase. Light travelling through space is stretched. This stretching does not just change wavelength, it changes how we interpret distance and time. Very distant galaxies appear not only faint but redshifted, their light pushed into longer wavelengths that require specialised instruments to detect. If we lacked infrared telescopes, much of the early universe would be invisible to us. Entire populations of stars would be missing from our counts. The development of new observational tools has repeatedly increased estimates of how many galaxies and stars exist, not because more stars suddenly appeared, but because we gained access to light that was always there. Even with modern instruments, there are stars we cannot see individually in distant galaxies. Their light blends together, contributing to a galaxy's overall brightness. Astronomers infer their presence statistically. They use models of stellar populations to estimate how many stars must be present to produce the observed light. This inference depends on assumptions about star formation, stellar lifetimes, and the distribution of star masses. Those assumptions are informed by nearby observations, where stars can be studied in detail. But there is always a leap involved. We assume that physics behaves the same everywhere, and evidence strongly supports that assumption. But the environments can differ. Early galaxies may have formed stars differently than modern ones. The first stars in the universe were likely very massive and short-lived. Their contribution to star counts is brief but intense. All of this means that when we look at the distant universe, we are seeing a star population that is not directly comparable to the one around us. It is younger, more dynamic, and sometimes fundamentally different in composition. Counting those stars requires careful adjustment. This adjustment is one of the reasons star counts are expressed as ranges rather than exact numbers. The uncertainty is not sloppy. It reflects the genuine complexity of the problem. Each layer of distance adds a layer of time. Each layer of time adds variation in conditions. Each variation adds uncertainty. There is also the matter of cosmic horizons. Beyond a certain distance, light has not had time to reach us. That region of the universe may contain stars, galaxies, and structures similar to those we observe, but they are currently inaccessible. They are not included in star counts of the observable universe. This does not mean they do not exist. It means they are beyond our observational boundary. This boundary is not fixed in space. It expands over time as light from more distant regions reaches us. The observable universe grows. That means the number of observable stars increases over cosmic time, even if the universe itself were static in star production, which it is not. So the star count we could make in the far future would be larger than the one we make today, simply because more light would have arrived. This dynamic aspect is rarely considered in casual discussions. The number of stars we can observe is not a final tally. It is a snapshot taken at a particular stage in cosmic history. Future observers would see more, past observers saw less. This realization adds a quiet humility to the question. We are not standing at the end of knowledge, looking back over a completed universe. We are midstream, receiving information gradually, limited by time and physics. There is also something deeply human about the experience of seeing old light. We are accustomed to associating sight with presence. When we see something, we assume it exists as we see it. In space, that assumption fails. Seeing becomes a form of time travel, passive but real. We receive information from the past constantly, without effort. This has an emotional resonance that doesn't need exaggeration. The stars are not just far away, they are ancient. The light entering your eyes tonight may have left its source before your ancestors existed. That light has survived cosmic expansion, dust, and chance, arriving now at this moment to be noticed or ignored. When scientists count stars, they are counting these surviving signals. Each counted star represents a successful transmission across vast time and space. Many stars have existed whose light never reached us, either because it was absorbed, scattered, or emitted in directions that missed Earth entirely. The universe contains more history than we can ever see. Understanding that helps reframe the question once again. How many stars are in the universe really is not just a numerical puzzle. It is a question about observation, limitation, and the relationship between existence and perception. The number we give is shaped by what we can see, not by what might exist beyond reach. Counting stars sounds at first like a task that should involve patience, sharp eyesight, and a very long checklist. One star, then the next, slowly building toward a total. But almost immediately that picture collapses. There are too many stars, too spread out, too distant, too faint, and too embedded in complex structures for direct counting to be anything other than symbolic. So scientists do something different. They estimate, and those estimations, when done carefully, turn out to be far more powerful than any impossible tally could ever be. To understand how scientists count stars without counting them, it helps to let go of the idea that science always works by direct enumeration. In many areas of knowledge, especially those involving enormous scales, indirect measurement is not a compromise. It is the only workable approach. You don't count every molecule in a glass of water to know how much water you have. You measure volume and density. You don't count every grain of sand on a beach. You sample a small area and extrapolate. Star counting works the same way, but with additional layers of complexity introduced by distance, time, and visibility. The foundation of stellar estimation begins close to home. Astronomers start with regions of space where stars can be observed individually and in great detail. The neighborhood around the Sun is one such region. Within a few hundred light years, telescopes can detect stars down to very low brightness levels. In this local volume, scientists can build what is essentially a census. They identify stars, measure their brightness, determine their masses, and classify them by type. This local census reveals something immediately important. Stars are not evenly distributed by brightness or mass. The vast majority of stars are small and faint. Red dwarfs dominate the population. They burn slowly, shine weakly, and live for trillions of years. Brighter stars, the ones that stand out in the night sky, are comparatively rare. They are massive, burn through their fuel quickly, and die young on cosmic timescales. If you were to count stars based only on what you can see with the naked eye, you would miss most of them. This realization shapes every subsequent estimation. Light is not a reliable proxy for number unless corrected. A small number of bright stars can dominate the light output of a region, masking the presence of far more numerous faint stars. So astronomers develop what are called stellar population models. These models describe how many stars of different masses and brightnesses are expected to exist in a given population, based on known physical processes of star formation. Once these distributions are understood locally, they become tools for interpreting distant observations. When astronomers observe a distant star cluster or galaxy, they often cannot see its faint stars individually, but they can measure the total light emitted. Using population models, they can estimate how many stars of different types must be present to produce that light. This process is not guesswork. It is constrained by physics. Stars of a given mass produce predictable amounts of light over their lifetimes. This approach turns brightness into a statistical signal rather than a direct count. Instead of asking how many points of light are visible, astronomers ask what combination of stars would most plausibly generate the observed glow. Different combinations are tested against models, and those that do not fit known stellar behaviour are discarded. The same logic applies within the Milky Way on larger scales. Astronomers divide the galaxy into regions based on distance, direction, and structure. In each region, they count the stars that are visible above a certain brightness threshold. Then they correct for stars that are too faint to detect, using the known distribution of star types. They also correct for dust obscuration, which hides stars behind clouds of gas and dust. Dust is a particularly stubborn complication. It does not block all light equally. It absorbs and scatters shorter wavelengths more effectively than longer ones. This means that optical surveys miss stars that infrared surveys can detect. So astronomers combine data from multiple wavelengths to build a more complete picture. Each wavelength fills in gaps left by the others. Even then, the view is incomplete. Some regions of the galaxy remain difficult to observe. The galactic centre, for example, is crowded, dusty and complex. Individual stars overlap in images, blending together. Specialised techniques are required to disentangle them. Infrared observations help, but even they have limits. So again, estimation steps in. Astronomers measure star density in regions that are easier to observe and use models of galactic structure to infer how density changes toward more difficult regions. These models are refined continuously as new data becomes available. Over time, the estimates become more robust, even if they never become exact. When scientists move beyond the Milky Way, direct star counting becomes almost entirely impossible. Individual stars can only be resolved in the nearest galaxies. Beyond that, galaxies appear as unified objects. Their stars merge into a continuous distribution of light. But the same principles apply. Total brightness, colour, and spectral features reveal information about stellar populations. Colour is especially useful. Different types of stars emit light differently across wavelengths. A galaxy dominated by young, massive stars looks bluer. One dominated by older, cooler stars looks redder. By analysing a galaxy's colour and spectrum, astronomers can infer the ages and types of stars it contains. From there, they estimate how many stars must be present. Mass provides another route. Galaxies rotate. The speed of that rotation reveals how much mass they contain. Some of that mass is in stars, some is in gas, some is in dark matter. By estimating the fraction of mass in stars, astronomers can convert total mass into an estimated star count. This method comes with its own uncertainties, but it provides an independent check on estimates derived from light alone. Importantly, these different methods often converge. Estimates based on brightness, colour, and mass tend to agree within a certain range. When independent approaches point to similar numbers, confidence grows. This convergence is one of the strongest indicators that the estimation process is working. It's also worth emphasising that scientists are not trying to produce a dramatic number for its own sake. The goal is not to impress. The goal is to constrain models of how the universe formed and evolved. Star counts feed into theories of galaxy formation, chemical enrichment, and cosmic structure. If the numbers were wildly wrong, many other predictions would fail. The fact that models remain consistent across multiple lines of evidence suggests that the estimates are broadly correct, even if they are not precise. Another key aspect of estimation is sampling. Astronomers rarely rely on a single observation. They survey many regions in many directions at many depths. This reduces the impact of local anomalies. A particularly dense region does not skew the overall picture if it is balanced by observations elsewhere. Over time, a statistical average emerges. This averaging process is crucial when dealing with cosmic structures. The universe is clumpy, galaxies cluster together, voids stretch between them, star formation is uneven, any small sample will be biased. Large samples smooth out those biases. Estimation thrives on repetition. Computer simulations also play a growing role. Cosmological simulations model the evolution of matter from the early universe to the present day. They include gravity, gas dynamics, star formation, and feedback processes. When these simulations produce galaxy populations that resemble what we observe, they provide additional confidence in our understanding. The simulated star counts can be compared to observational estimates, offering another layer of validation. Of course, simulations depend on assumptions. They are not reality, but they are grounded in well-tested physical laws. When simulations and observations align, it suggests that the assumptions are reasonable. One might wonder whether all this indirect work introduces too much uncertainty to be meaningful, but the opposite is true. Indirect measurement, when constrained by multiple independent factors, can be remarkably reliable. It allows scientists to tackle questions that would otherwise be inaccessible. There is also a philosophical aspect to this approach. Estimation acknowledges uncertainty openly. Instead of pretending to know more than is possible, scientists define what they know within limits. They give ranges, not absolutes. They revise estimates as new data arrives. This flexibility is not weakness, it is strength. In everyday life, estimation often carries a negative connotation. It suggests approximation, guesswork, lack of rigor. In science, especially at large scales, estimation is the rigorous approach. It is the disciplined translation of incomplete information into constrained understanding. When you hear that the observable universe contains on the order of 10 to the 22nd stars, that number is not the result of someone multiplying wildly large figures without care. It is the product of decades of observation, modelling, cross-checking, and revision. It is a summary of everything we currently know about galaxies, star formation, and cosmic history, compressed into a single statement. And even that statement is provisional. As telescopes improve, as surveys deepen, as models refine, the estimate may change. It may increase, it may decrease slightly, but it will not collapse entirely. The scale is robust, even if the exact value is not. Understanding this helps reframe the original question. How many stars are in the universe? Really, is not a question with a hidden exact answer waiting to be uncovered. It is a question whose answer sharpens over time, guided by evidence and bounded by physics. Counting without counting is not a workaround. It is the method. It is how science operates when direct access is impossible. And in the case of stars, direct access was never an option to begin with. When people hear the phrase, the observable universe, it often sounds like a technical footnote, a detail added to keep scientists honest. But in reality, it is one of the most important ideas in modern cosmology, especially when we try to answer questions about how many stars exist. The observable universe is not a casual subset of a larger whole. It is the only part of the universe that can, even in principle, be studied directly. Everything we know about stars on the larger scales lives inside this boundary, and everything beyond it exists in a different category altogether, one defined not by absence, but by inaccessibility. The observable universe is shaped by a simple but uncompromising rule. Light travels at a finite speed, and the universe has a finite age. Because of that, there is a maximum distance from which light has had enough time to reach us since the beginning of cosmic expansion. Any object farther away than that distance has not had time to send us information yet. It may exist. It may be filled with stars and galaxies indistinguishable from those we see nearby. but for now it is causally disconnected from us. We cannot see it. We cannot measure it. We cannot include it directly in any count. This boundary is not a wall in space. It is a horizon in time. As the universe ages, light from more distant regions gradually reaches us, and the observable universe grows. That means the volume of space we can observe increases over time, even if the universe itself has always been much larger. The observable universe today is larger than it was billions of years ago, and it will be larger still in the far future. But expansion complicates this picture. Space itself is expanding, stretching the distance between galaxies as time passes. Because of this, the current distance to the most distant observable regions is much larger than the simple product of the universe's age and the speed of light. Light that left those regions billions of years ago has been travelling through expanding space the entire time. By the time it arrives, the source is much farther away than when the light began its journey. This is why the observable universe has a radius measured in tens of billions of light years, even though the universe is only about 13.8 billion years old. The light did not travel through static space. Space expanded underneath it. Within this observable region lie all the galaxies we can detect, directly or indirectly. Every deep field image, every faint smudge catalogued by telescopes, every statistical inference about unseen galaxies applies only within this boundary. When scientists estimate the number of stars in the universe, they are almost always referring to the number of stars within the observable universe, not the entire universe in an absolute sense. This distinction matters more than it might seem at first. The observable universe is not guaranteed to be representative of the whole. On the larger scales, the universe appears remarkably uniform, but we cannot prove that conditions beyond our horizon are identical to those within it. We assume consistency based on physical laws and observed patterns, but assumption is not observation. Beyond the observable universe, certainty ends. This does not mean speculation runs wild. Cosmology is careful about how far it extrapolates. Theories about the universe as a whole are constrained by what we can observe locally and by well-tested physical principles. Still, the difference between what we can see and what may exist is fundamental. It defines the limits of scientific counting. Inside the observable universe, astronomers estimate that there are hundreds of billions, possibly trillions, of galaxies. Each of those galaxies contains stars. Some contain relatively few, others contain staggering numbers. When scientists estimate the total number of stars, they combine galaxy counts with estimates of how many stars different types of galaxies contain. The result is a number so large it defies everyday intuition, typically expressed as tens of sextillions. That number already feels almost absurdly large. But it is important to recognize that it is a lower bound on the total number of stars that exist, not an upper bound. It counts only the stars whose light has had time to reach us. It excludes everything beyond the observable horizon, so what lies beyond it? The honest answer is that we do not know directly, but we can discuss possibilities, constrained by theory and observation. One possibility is that the universe beyond the observable region is very similar to what we see within it. In this view, space extends far beyond our horizon, perhaps infinitely, populated by more galaxies, more stars, repeating the same large-scale structure we observe locally. If this is the case, then the total number of stars in the entire universe would be vastly larger than the already enormous number within the observable region. It might be infinite. Another possibility is that the universe is finite but extremely large. In that case, there is a total number of stars, but it lies far beyond any practical ability to count or even estimate directly. The observable universe would be a small sample of the whole, like a single grain taken from an enormous field. There are also more exotic possibilities, involving different physical conditions or topologies of space beyond our horizon. These ideas are explored in theoretical physics, but they remain speculative. Without observational access, they cannot be tested in the same way as models within the observable universe. What is important here is not which possibility is correct, but what they all have in common. Beyond the observable universe, star counting loses operational meaning. You cannot count what you cannot observe, even indirectly. You can hypothesize, you can model, but you cannot measure. This is why scientists are careful with their language. When they speak precisely, they specify the observable universe. When popular accounts drop that qualifier, confusion creeps in. People imagine that the quoted number represents everything that exists, when in fact it represents everything we can currently access with light. The observable universe also has internal structure that affects star counts. It is not uniformly filled with galaxies. Galaxies cluster together. Vast voids stretch between clusters. Some regions are dense, others are sparse. When astronomers sample the universe, they must account for this unevenness. A deep observation of one region may not be representative of another. To address this, surveys cover large areas of the sky and sample many different environments. The goal is not to map every galaxy individually, which would be impossible, but to understand statistical distributions. How many galaxies exist per unit volume? How that number changes with distance? How galaxy types vary across environments? These distributions feed directly into star count estimates. As observations push deeper, they reveal galaxies at earlier and earlier stages of cosmic history. Some of these early galaxies are small and irregular. Some are surprisingly massive. Many are forming stars at rates far higher than typical modern galaxies. This tells us that star formation was more intense in the past, which affects how many stars existed at different times. When astronomers integrate star formation over cosmic time within the observable universe, they can estimate how many stars have formed in total. Many of those stars no longer exist. They have ended their lives, but their contribution matters for understanding the universe's history. This integration across time and space is another reason star counts are expressed carefully. A number like 10 to the 22nd stars does not represent a frozen snapshot of the universe at one moment. It represents an estimate of the number of stars contained within the observable universe, based on present-day populations inferred from light emitted across billions of years. Beyond the observable universe, that integration cannot be performed. We do not know the star formation history there. We do not know how matter is distributed. We do not know whether the same processes apply unchanged. Any attempt to count stars beyond the observable universe would rely entirely on extrapolation, not evidence. This boundary also intersects with deeper philosophical questions about what it means for something to exist in a scientific sense. In everyday language, existence feels absolute. Something either exists or it does not. In cosmology, existence and observability are intertwined. An object beyond the observable universe may exist, but it has no causal connection to us. It cannot affect us, and we cannot affect it. In that sense, it sits outside the domain of empirical science, at least for now. That does not make it meaningless. It simply places it in a different category. Science describes what can be observed, measured, and tested. The observable universe defines that domain. Beyond it lies a realm where science can propose models, but not confirm them directly. Understanding this helps ground the discussion of star counts. When someone asks how many stars are in the universe, the most rigorous answer is not a single number, but a layered explanation. There are at least this many stars within the observable universe. There may be far more beyond it. We do not currently know. This uncertainty is not a flaw in our understanding. It is a reflection of the universe's structure and our position within it. We are observers embedded in space and time, receiving information at a finite speed. Our knowledge grows as light arrives. There is also a quiet symmetry here. Just as individual stars have horizons defined by how far their light can travel before fading, The universe itself has a horizon defined by age and expansion. Everything we know arrives as light, and everything we do not know remains unlit for now. As technology improves, the boundary of the observable universe will not move outward dramatically, but our ability to extract information from its depths will improve. We will detect fainter galaxies. We will refine star formation histories. We will reduce uncertainties. But the fundamental horizon will remain. This is why the observable universe is not just a technical term. It is the stage on which all cosmic counting plays out. It defines what questions can be answered with evidence and which ones remain open. There is a moment, usually somewhere in the middle of a conversation about the universe, when numbers stop helping and people reach for comparison instead. Trillions, sextillions, powers of 10, all of it begins to blur together. The mind looks for something solid, something familiar, something it can hold or picture. And that is when the comparison appears, almost inevitably. There are more stars in the universe than grains of sand on Earth. It's a sentence that sounds definitive, comforting even, as if it pins an unfathomable number to something tangible. But like many simple statements about vast things, it deserves to be examined slowly and carefully. At first glance, the comparison feels clever. Everyone has seen sand. Many people have walked on beaches, scooped handfuls of it, let it run through their fingers. Sand is numerous in a way that feels overwhelming at a human scale. You can't count it. You can't keep track of it. It stretches across coastlines, deserts, riverbeds. It feels endless. So when someone says there are more stars than grains of sand, the mind nods. That sounds about right. Big meets big. But the usefulness of the comparison depends on what question it is trying to answer. If the goal is to convey that the number of stars is extraordinarily large, then the comparison succeeds. It communicates scale emotionally, not mathematically. It signals that we are well beyond everyday quantities. But if the goal is to be precise, or even carefully approximate, the comparison becomes less straightforward. To understand why, it helps to break the statement into its parts. First, how many grains of sand are there on Earth? Second, how many stars are there in the observable universe? And third, are these two quantities even comparable in a meaningful way? Let's start with sand, because it feels familiar. Sand grains are small, but they are not uniform. Their size varies depending on location, composition, and erosion processes. Beach sand differs from desert sand. River sand differs from volcanic sand. Some grains are smooth and rounded. Others are angular. Their diameters can vary by orders of magnitude. This matters because when you count grains of sand, the size of the grain determines how many fit into a given volume. So when scientists attempt to estimate the number of grains of sand on Earth, they do not count them individually, obviously. They estimate the total volume of sand and divide by an estimated average grain volume. This already introduces uncertainty, but it is manageable within ranges. Next comes the question of where sand exists. Beaches are the most obvious source, but they are not the only one. Deserts contain vast quantities of sand, much of it far from coastlines. River deltas contribute, inland dunes, submerged sands on the ocean floor. Not all sand is easily accessible or even visible. Some is buried, some is compacted, some is constantly shifting. So even before assigning numbers, we are dealing with an estimate built on assumptions about distribution and depth. How deep do we count? Do we include sand-buried meters below the surface? Do we include underwater sediments? Different estimates include different assumptions, and the totals can vary accordingly. Despite this, scientists have made reasonable attempts to estimate the number of grains of sand on Earth. These estimates often land around numbers on the order of 10 to the 18th or 10 to the 19th grains. That is a 1 followed by 18 or 19 zeros. It is a staggeringly large number, but it is finite, and it is constrained by the size of the planet and the processes that create sand. Now let's turn to stars. Estimates of the number of stars in the observable universe often land around 10 to the 22nd or 10 to the 24. That is several orders of magnitude larger than most sand estimates. On paper, this suggests that yes, there are more stars than grains of sand. But the comparison is not quite that simple. First, star estimates are not counts of objects on Earth. They are estimates of objects spread across an expanding universe, inferred from light that arrives over billions of years. They depend on models of galaxy populations, star formation histories, and observational limits. They are not direct tallies, and their uncertainty spans orders of magnitude. Second, sand estimates are bounded by Earth. We know the size of the planet. We know roughly how much of its surface is covered by sand-rich environments. We can sample and extrapolate. The uncertainty is significant, but the domain is limited. Star estimates, by contrast, are bounded only by the observable universe, which itself is a moving boundary, defined by time and expansion. Third, the comparison implicitly treats stars and grains of sand as equivalent units of counting. But they are not equivalent in how they are distributed or defined. A grain of sand is a discrete object with clear boundaries. A star is also a discrete object, but what counts as a star is not always obvious. Do stellar remnants count? Do brown dwarfs count? Do stars that no longer exist but whose light is still arriving count? Different definitions yield different totals. This doesn't mean the comparison is meaningless. It means it should be understood for what it is. It is not a precise statement. It is a rhetorical bridge between the human-scale world and the cosmic-scale world. There is another subtle issue. The comparison often implies a kind of competition. More stars than grains of sand. Which is bigger? Which wins? But this framing misses the deeper point. Both numbers are unimaginably large relative to human experience. The difference between 10 to the 19th and 10 to the 22nd is vast mathematically, but emotionally both are beyond intuitive grasp. This is why the comparison persists. It is not about exactitude. It is about anchoring wonder. It gives the mind a place to stand, even if that place is approximate. However, when used without context, the comparison can create misconceptions. Some people take it to mean that the universe is completely understood, that we have counted everything and declared victory. Others imagine stars scattered evenly like sand grains, which misrepresents the structured nature of the universe. Stars cluster into galaxies. Galaxies cluster into larger structures. Sand does not behave that way. There is also the issue of visibility. People have seen sand in large quantities. No one has seen stars in comparable numbers directly. The night sky shows only a tiny fraction of the stars in our own galaxy, let alone the universe. So the comparison bridges a gap in experience, but it also glosses over the vast difference in how we encounter these quantities. Another point worth considering is that sand is static on human timescales. The number of grains on Earth changes slowly, through erosion, deposition, and geological processes. But over thousands of years, the total remains roughly similar. Stars, by contrast, are dynamic. They form. They die. The number of stars in the universe changes over cosmic time. When we compare stars to sand, we are comparing a snapshot of a dynamic system to a relatively stable one. There is also a deeper philosophical layer. Sand is local. It belongs to Earth. Stars belong to the universe. Comparing the two subtly links our small world to the largest possible context. It reminds us that the same physical reality contains both beaches and galaxies, both grains and suns. That connection is part of why the comparison resonates. But if we slow down and ask whether the statement is literally true, the honest answer is nuanced. Based on current estimates, there may indeed be more stars in the observable universe than grains of sand on Earth. But both numbers are uncertain. Both depend on assumptions, and both are subject to revision as knowledge improves. It is also important to remember that the observable universe is not the entire universe. If the universe extends far beyond what we can see, and if it contains stars beyond our horizon, then the total number of stars could be vastly larger than any sand-based comparison. In that case, the comparison becomes almost trivial. Of course, there are more stars. There could be infinitely more. On the other hand, if the universe is finite and structured differently beyond our horizon, the total could be bounded. We simply do not know. The comparison, then, is constrained by our observational limits. What the comparison really reveals is how humans cope with scale. When faced with numbers that exceed comprehension, we reach for metaphors rooted in experience. We use sand, grains, beaches, deserts, because these are things we have touched. The comparison is less about accuracy and more about translation. This translation is useful, but it has limits. At some point, comparisons flatten differences rather than clarify them. A grain of sand and a star are both countable objects, but they occupy radically different roles in physical reality. A grain of sand does not shape its surroundings through gravity, radiation, and nuclear processes. A star does. Comparing them numerically ignores those qualitative differences, and yet the comparison endures because it speaks to a shared sense of awe. It tells us that the universe is not just large, but extravagantly so. It suggests that abundance is a fundamental feature of reality, not an exception. Perhaps the most important thing to take away from this comparison is not whether it is strictly true, but why it matters to us that it might be. We want to know where we stand. We want to place ourselves between the smallest things we know and the largest things we can imagine. Sand and stars become bookends in that mental map. When you walk on a beach and feel the sand shift under your feet, you're interacting with a number so large it defies counting. When you look up at the night sky and see a scattering of stars, you're glimpsing a number far larger still, mostly hidden. The comparison links those two experiences, reminding us that the same universe contains both. It becomes clear that comparisons like this are stepping stones rather than destinations. They help us approach the question, but they do not answer it fully. At some point in this long exploration, a number finally takes shape. It might be written as a power of 10, stretched across the page with more zeros than feel comfortable. It might be spoken aloud carefully, slowly, as if pacing matters. Tens of sextillions, 10 to the 22nd. Something in that range, and for a moment it can feel like the journey is complete. The universe has been quantified, the stars have been counted, at least in principle. The question seems answered, but that feeling doesn't last long because a number like this does something strange. Instead of settling the mind, it unsettles it. It invites follow-up questions that are quieter but deeper. What does this number actually mean? What can it tell us? And just as importantly, what can it not tell us, no matter how large or carefully derived it is? The first thing to understand is that the number itself is not an object. It is a summary. It compresses an enormous amount of information into a single expression. Inside that number live assumptions about galaxy counts, star formation rates, stellar lifetimes, cosmic expansion, observational limits, and statistical corrections. The number is not a discovery in the same way a new planet or a new particle is a discovery. It is a synthesis, a conclusion drawn from many strands of evidence woven together. Because of that, the number carries context with it. Whether or not that context is spoken aloud, it means, based on what we can currently observe, model and infer within the observable universe, given our best understanding of physics, this is the approximate scale of stellar abundance. That is a long sentence, and in everyday conversation it gets shortened to a single figure. But the long sentence never really goes away. It is always implied. This is why the number should not be treated as a fact carved into reality. It is not the universe's official inventory. It is a reflection of our current relationship with evidence. If our instruments improve, if our models change, if new observations challenge old assumptions, the number will change too. Not wildly, perhaps, but meaningfully, and that is not a problem. That is how knowledge works at this scale. One thing the number does mean is abundance. It tells us that stars are not rare. They are not precious anomalies sprinkled sparingly through space. They are common outcomes of cosmic processes. Given gas, gravity and time, stars form readily. The universe is efficient at producing them. Whatever else might be said about cosmic emptiness, the raw material for light and structure has been used generously. This abundance reshapes older intuitions. For much of human history, stars felt distant, unreachable, and few. The night sky showed only a limited sample, and it was easy to imagine those points as special, singular beacons. The number reminds us that what we see is not representative. The visible stars are the exception, not the rule. Most stars are faint, distant and unseen without instruments. The universe is filled with them quietly. The number also means that our galaxy is not special in its richness. The Milky Way is impressive from the inside, but it is one example among countless others. Its hundreds of billions of stars contribute to the total, but they do not dominate it. Many galaxies match it. Some exceed it. Some fall far below it. Taken together, they form a population where no single system defines the whole. In that sense, the number is a corrective. It pushes back against the tendency to center our local environment as the standard. It reinforces a broader lesson that astronomy has delivered repeatedly over centuries. We're not at the center. We're not the largest. We're not the most typical. We are part of a distribution. Another thing the number means is that the universe operates comfortably at scales far beyond human concern. Stars form and die whether or not anyone notices. Galaxies assemble and merge without reference to observers. The processes that generate these vast quantities do not require intention or design. They arise from physical laws applied consistently over enormous spans of time and space. This realization can feel impersonal at first, but it also carries a kind of reassurance. The universe does not need to be managed. It does not rely on fragile conditions to persist. It is robust, prolific, and self-sustaining on scales that dwarf individual lifetimes. However, there are many things the number does not mean, and these are just as important to acknowledge. It does not mean that we understand every star. Knowing how many stars exist does not tell us where they all are, what they are like individually, or what systems they host. The vast majority of stars will never be studied in detail. They will never be named, catalogued, or characterized beyond statistical inclusion. The number is not a map. It is a measure of scale. It also does not mean that the universe is evenly populated. Abundance does not imply uniformity. Stars cluster. They gather into galaxies. Galaxies gather into filaments. Voids stretch between them. Some regions teem with star formation. Others are quiet and sparse. The number smooths over this structure. It tells us how much, not how arranged. The number does not tell us how many stars have planets, how many planets might host life, or how common complex systems are. Those questions depend on additional layers of probability. They require knowledge about planetary formation, chemistry, stability, and biology. While the number of stars sets the stage for those discussions, it does not resolve them. It is tempting to take a very large number of stars and leap directly to conclusions about inevitability. If there are so many stars, surely everything that can happen must have happened somewhere. Surely life must be common. Surely intelligence must arise repeatedly. These ideas are emotionally appealing, but they are not guaranteed by star counts alone. Abundance increases opportunity, but it does not dictate outcome. The number also does not mean that the universe is comprehensible in the way smaller systems are. Large quantities do not automatically become simpler when averaged. Sometimes they become more complex. Emergent behavior, rare events, and long-tail distributions can dominate outcomes even in vast populations. Knowing the size of the population is only the beginning of understanding its behavior. Another thing the number does not mean is that we are insignificant in a dismissive sense. It is easy to hear enormous numbers and conclude that individual existence is trivial by comparison. But scale does not determine value. The fact that there are countless stars does not negate the significance of a single experience, a single consciousness, or a single moment of awareness. Those things operate on different axes entirely. The universe can be vast without being hostile to meaning. The number of stars describes physical abundance, not experiential worth. Confusing the two leads to unnecessary despair or detachment. They are not competing measures. There is also a subtle misunderstanding that sometimes accompanies large numbers. People assume that because the number is so big, it must be exact, or at least fixed. But as we have seen, it is neither. It is an estimate bounded by what we can observe. It shifts as the observable universe grows, as new galaxies are detected, as models refine. Treating it as static misunderstands its nature. The number also does not mark an endpoint. It does not close the question. If anything, it opens more doors. How did so many stars form? Why did star formation peak when it did? How will the number change in the far future as star formation slows and existing stars age and fade? What happens to the universe when the lights begin to go out one by one over unimaginable spans of time? These questions are not answered by the number, they are prompted by it. There is another layer that often goes unnoticed. The number does not exist independently of us. It is not floating out there in space. It is a product of human inquiry. It exists because we asked the question, built the tools, developed the models, and decided how to summarize what we found. In that sense, the number reflects as much about us as it does about the universe. It reflects our curiosity, our patience, our willingness to grapple with things we cannot touch. It reflects the collective effort of generations of observers and thinkers, each adding a small piece to a much larger picture. The number is not just cosmic, it is cultural. This is why reducing it to a trivia fact does it a disservice. When treated as a fun statistic, it loses its depth. It becomes something to be memorized rather than contemplated. But when treated as a boundary marker between the known and the unknown, it regains its power. Another thing the number does not mean is completeness. Even within the observable universe, there are stars we cannot detect individually or even collectively with current instruments. Some are too faint, some are hidden behind dust. Some belong to galaxies too small or diffuse to be detected. Corrections account for them statistically, but they remain unseen. The number includes them in principle, not in practice. And beyond the observable universe, the number tells us nothing at all. There may be more stars than we can currently estimate. There may be structures far beyond our horizon. The number does not cap reality. It caps knowledge. This distinction matters because it shapes how we relate to the universe. If we believe the number represents everything, we risk mistaking our perspective for totality. If we understand it as a boundary of observation, we remain open to revision and expansion. There is also a quiet emotional effect to very large numbers that deserves acknowledgement. After a certain point, scale stops inspiring awe and starts inducing numbness. The mind cannot hold the quantity, so it disengages. This is not a failure, it is a protective mechanism, but it means that numbers alone are not sufficient to convey meaning. Meaning comes from context, from relationships, from understanding what a number can and cannot say. The number of stars is meaningful because it tells us something about how the universe behaves. It is not meaningful because it is large. In practical terms, scientists rarely work directly with the total number of stars. It is not a number they plug into equations regularly. They work with densities, rates, distributions. The total is a derived quantity, useful for communication and broad understanding, but not the engine of daily research. That alone should signal that its role is interpretive rather than operational. So where does that leave us? The number means that the universe is vast, prolific, and structured. It means that stars are common outcomes of cosmic evolution. It means that our local environment is one example among many. It means that observation is limited by time and physics. It means that knowledge grows incrementally. What it does not mean is that we have finished understanding. It does not mean that everything important has been quantified. It does not mean that individual existence is diminished. It does not mean that mystery has been eliminated. In many ways, the most honest role of the number is as a signpost. It marks how far we have come in understanding scale, and how far there is still to go in understanding meaning. After grappling with vast quantities and abstract totals, the question turns inward. How does a human mind, living on one planet around one star, relate to a universe described in numbers this large? How does scale affect perspective, emotion, and identity? There is a quiet tension that emerges once the numbers have been spoken and then allowed to settle. Tens of sextillions of stars, galaxies by the hundreds of billions, distances measured in billions of light years. After a while, the mind naturally turns back towards something much smaller, not out of avoidance, but out of necessity. Where does a human fit into all of this? How does a life measured in decades relate to a universe, measured in billions of years and filled with more stars than language can comfortably express? This question is not scientific in the narrow sense, but it is inseparable from science at this scale. Astronomy does not exist in a vacuum. It is practiced by people with bodies, limits, attention spans, and emotional responses. When we talk about human scale in a star-filled universe, we are not diminishing the science. We are completing it by acknowledging the perspective from which all of this knowledge arises. Human scale is defined by proximity, duration, and perception. We understand what we can interact with directly: a room, a street, a landscape, a lifetime. These are the units our intuition evolved to handle. Even when we learn about larger systems, we often translate them back into these terms. We ask how long something would take to travel. We ask how many lifetimes would fit into a given time span. We ask how many Earths could fit inside a star. These translations are attempts to anchor understanding in experience, but stars resist that anchoring. No matter how many metaphors we stack, they remain outside direct experience. We do not feel their gravity. We do not see their surfaces unaided. We do not witness their life cycles unfold. We encounter them only through light, filtered by distance and time. That distance creates a psychological gap that is easy to misinterpret. One common response to this gap is a sense of insignificance. Faced with such vastness, some people feel reduced, as though scale itself were a measure of worth. If the universe is so large, and we're so small, then perhaps we do not matter. This conclusion feels intuitive, but it does not follow logically. Size and significance are not the same kind of property. A virus can reshape ecosystems. A thought can alter a life. Scale does not dictate consequence. Another response is detachment. The numbers feel so large that they seem abstract, irrelevant to daily life. Bills still need to be paid, bodies still get tired, relationships still require attention. Against those immediate concerns, the number of stars can feel like trivia, impressive but disconnected. This response is also understandable. Human attention is finite. It prioritizes what affects survival and connection. But there is a third response, quieter and less often articulated: perspective. When allowed to unfold slowly, without pressure to conclude anything dramatic, cosmic scale can soften the edges of human concern, not by making problems disappear, but by placing them in a broader context. This does not trivialize difficulty. It reframes it. Human scale becomes clearer when contrasted gently, not violently, with cosmic scale. A human life is brief compared to stellar lifetimes, but that brevity gives it a particular intensity. Stars burn steadily for millions or billions of years. Humans experience rapid change, growth, learning, loss, adaptation. Time is dense at our scale. A decade can contain transformation that would be imperceptible on a cosmic clock. In this sense, smallness is not a deficit, it is a mode of operation. Humans are not designed to persist unchanged for eons. We are designed to respond, to notice, to care. Those qualities do not compete with cosmic processes, they exist alongside them. There is also the matter of location. We exist on one planet, orbiting one star within one galaxy. That specificity is sometimes framed as limitation, but it is also what makes observation possible. You cannot stand everywhere at once. You must stand somewhere. From that somewhere, you look outward. All knowledge begins from a position, not from nowhere. Astronomy often emphasizes how uncentral our location is, and rightly so. We are not at the center of the galaxy. The galaxy is not at the center of the universe. There is no privileged cosmic location. But non-central does not mean irrelevant, it means representative. The physical laws we observe here appear to apply everywhere we can test them. The processes that formed our star operate throughout the cosmos. In that sense, our local experience is not special, but it is informative. Human scale also determines how we encounter numbers. A number like 10 to the 22nd stars cannot be felt. It cannot be visualized. It can only be symbolized. When we try to imagine it, the mind either collapses it into a vague sense of a lot, or disengages entirely. This is not a failure of intelligence, it is a boundary of cognition. Recognizing that boundary is important, because it frees us from the need to force comprehension where it is not possible. We do not need to feel the number to understand its implications. We can work with relationships instead. More than, far greater than, orders of magnitude beyond. These relational concepts are enough to guide reasoning without demanding impossible mental images. Human scale also shapes how we ask questions. We tend to ask questions that have relevance to experience. How far? How long? How many? These questions become harder to answer meaningfully as scale increases. At some point, the answer becomes less about the quantity itself and more about the method used to arrive at it. This is why discussions of star counts inevitably lead to discussions of observation, estimation, and limitation. From a human perspective, knowing how many stars exist is less important than knowing that stars exist at all, and that their existence follows understandable patterns, that they form from gas, shine through fusion, and return their material to space, that those processes created the elements that make up planets and bodies. In that chain, human existence is not separate from stellar existence. It is downstream from it. Every atom heavier than hydrogen in your body was forged in a star. Not metaphorically, literally. Carbon, oxygen, calcium, iron. These elements were produced through stellar processes long before the sun formed. They were scattered into space by dying stars and later incorporated into new systems. Human scale emerges from cosmic scale in a direct material way. This connection is often stated quickly, but it deserves to be lingered with. It means that the vast number of stars is not just a backdrop, it is a history of production. The abundance of stars corresponds to the abundance of the elements that make complex structures possible. A universe with far fewer stars would be chemically poorer. A universe with no stars would be inert. So when we talk about a star-filled universe, we're also talking about a universe capable of producing complexity. That complexity includes galaxies, planets, atmospheres, chemistry, and eventually organisms that can ask questions about stars. Human scale is not an afterthought, it is an outcome. This reframes the emotional response to vastness. Instead of seeing scale as something that diminishes us, we can see it as something that enables us. The same processes that produce trillions of stars also produce the conditions for localized awareness. Awareness does not need to be large to be meaningful. It needs to be situated. Another aspect of human scale is attention. We cannot attend to everything at once. We focus on small portions of reality at a time. This is true in daily life and in science. Astronomers do not study the entire universe at once. They study specific objects, Specific regions, specific questions. They build understanding piece by piece. The total number of stars is not something anyone holds in mind continuously. It is a reference point, not a working object. Most astronomical research proceeds without invoking it at all. Human scale governs how knowledge is produced. Large-scale conclusions are assembled from many small-scale investigations. This piecemeal approach mirrors human experience more generally. Lives are lived moment by moment, not all at once. Meaning accumulates through sequences, not totals. Asking how many stars exist is analogous to asking how many moments make up a life. The answer is large, but the experience is granular. There is also the question of expectation. When people hear about the vast number of stars, they often leap to expectations about contact, discovery, or destiny. Surely with so many stars, something must happen. Surely we're not alone. These expectations are understandable, but they arise from human narrative instincts rather than evidence. They reflect our tendency to project significance outward. The universe does not owe us company. It does not promise outcomes based on scale alone. It provides conditions. What emerges from those conditions depends on many factors. Human scale reminds us to separate possibility from inevitability. At the same time, human scale allows for hope without certainty. The abundance of stars increases the number of opportunities for complex systems to arise. It does not guarantee anything, but it widens the space of possibility. That widening is meaningful, even if it remains unresolved. Another subtle effect of cosmic scale is how it reshapes time perception. Human concerns often feel urgent because time feels scarce, and it is. But when placed against cosmic timescales, urgency and scarcity take on a different texture. Some things feel less pressing, others feel more precious. A conversation, a quiet moment, a shared experience. These are brief, and therefore valuable. This is not about minimizing struggle or difficulty. It is about recognizing that human meaning operates on a different axis than cosmic duration. Stars can burn for billions of years without caring. Humans care intensely for much shorter spans. That caring is not invalidated by comparison. It is defined by it. Human scale also governs how we use knowledge. Knowing about stars does not change how gravity works on Earth. It does not alter daily routines directly. Its influence is indirect. It shapes worldview. It alters perspective. It can inspire, unsettle, or calm. Those effects matter, even if they are not measurable in equations. When astronomy is approached slowly, without pressure to extract grand conclusions, it often has a quieting effect. The mind steps back. Immediate concerns loosen their grip slightly. This does not solve problems, but it can make them easier to carry. Human scale benefits from occasional reminders that not everything demands resolution right now. In that sense, a star-filled universe can be a place of rest rather than intimidation. The stars are not watching. They are not judging. They are simply there, following physical laws indifferent to human worries. That indifference can feel cold, but it can also feel relieving. The universe does not amplify our anxieties. It contains them. Understanding human scale within this context is not about drawing moral lessons from physics. It is about aligning expectations. The universe is vast. Humans are limited. Both statements can be true without conflict. After travelling outward through layers of distance, time, and number, there is a natural pull to return to where we started. Not because the outward journey was too much, or because the universe suddenly becomes less interesting, but because understanding gains meaning when it reconnects with the place from which the question was asked. We began by looking up. It makes sense to end by looking around, and then up again, from the ground beneath our feet, under the same sky that quietly holds everything we have been talking about. No matter how far the imagination wanders, the body remains here. Breathing happens here. Gravity holds us here. The room you are in, the surface supporting you, the sounds around you, all continue unchanged while the mind moves across billions of light years. That contrast is not a failure of imagination. It is a reminder that thought and presence operate at different scales, and both are real. The stars do not recede when we stop thinking about them. They do not approach when we focus on them. They remain where they are, following paths set by gravity and time. The universe does not respond to attention, and yet attention changes how we experience the universe. That is the quiet paradox at the heart of this entire exploration. When we first asked how many stars there are, the question felt outward-facing, expansive, almost abstract. It pointed away from Earth, away from the familiar. But now, having traced the reasoning behind the estimates, the limitations of observation, the layers of time embedded in light, and the immense scales involved, the question begins to feel different. It no longer pulls us away. It settles back into place, connected to the same everyday reality it emerged from. The number of stars does not hover above us like a weight. It does not press down on human life. It exists as background knowledge, something that can be revisited or set aside without consequence. You can live an entire life without thinking about it at all, and the universe will not notice. That fact is sometimes framed as bleak. It does not have to be. Indifference from the universe does not imply indifference within it. Meaning, care, and experience arise locally. They do not require cosmic endorsement. A star does not need to acknowledge a human life for that life to matter to the person living it, or to others connected to it. The universe is vast enough to hold countless stars and still leave room for quiet moments on a single planet. When people talk about being just a speck in a star-filled universe, the phrase is often delivered with a sense of finality, as if smallness were the last word. But smallness is only one dimension. A speck can still be complex. It can still host experience. It can still be the center of its own frame of reference. From where you are right now, Earth is not small. It is everything. Looking back down to Earth does not undo what we have learned about scale. It integrates it. The ground beneath you is part of a planet that formed from the same cosmic processes that formed stars. The elements in the soil, the air, and your body were forged in stellar interiors long before the sun existed. This is not poetic framing. It is physical continuity. Every time you look at the night sky, you're not looking at something separate from yourself. You're looking at a larger context of the same material reality. The distance is real, but the connection is also real. Both coexist without cancelling each other out. There is something quietly stabilizing about that realization. The universe is not a distant abstraction. It is the larger environment in which Earth happens to exist. The stars are not decorations. They are participants in the same physical story, operating on scales that dwarf human life, but feeding into it nonetheless. When astronomers estimate how many stars exist, they are not standing outside the universe, clipboard in hand. They are doing this work from planets, around stars, inside galaxies. The act of counting is itself a local phenomenon carried out by beings who evolved under specific skies, using tools built from local materials. Even the most expansive knowledge begins somewhere specific. That specificity matters. It grounds the entire discussion. We are not detached observers floating in neutral space. We are inhabitants of a particular place, asking questions outward from that place. There is no shame in that. It is the only way observation ever works. As this exploration winds down, the stars themselves have not changed. They have not grown more numerous or fewer. What has changed, perhaps, is how they sit in the mind. The question, how many, has unfolded into a broader understanding of how, within what limits, and from where. It becomes clear that the value of the question was never in arriving at a number alone. The value is in tracing the reasoning, the boundaries, and the assumptions behind that number. It was in recognizing where certainty ends and estimation begins. It was in seeing how observation is shaped by time, distance, and technology. And now, having followed that path, it is natural to let the question rest. You do not need to hold on to the figures. You do not need to remember powers of 10 or ranges of uncertainty. Those details are not the takeaway. They are scaffolding useful while building understanding, but not necessary to keep once the structure stands. What remains is a simpler awareness. The sky above you is filled with stars, far more than you can see, far more than you can imagine individually. They exist whether or not they are counted. They follow physical laws whether or not they are contemplated. Their abundance does not demand anything from you. At the same time, the act of wondering about them is distinctly human. Other animals navigate by the stars, respond to light cycles, or orient themselves in relation to the sky. But asking how many stars exist, constructing tools to estimate that number, and reflecting on what it means, that is something humans do. Not because it is required, but because curiosity arises naturally when awareness meets vastness. That curiosity does not need to be resolved fully to be satisfying. In fact, some questions are better companions than destinations. They can be revisited at different times, from different emotional states, without ever being exhausted. As you rest under the same sky that has always been there, it may help to remember that every generation before this one asked similar questions with fewer tools and less information. They still found meaning in looking up. Future generations will ask the same questions with better instruments and new frameworks. They will refine the numbers, adjust the models, and discover details we cannot yet imagine. And still, the basic experience will remain the same. A person, somewhere on Earth, looking up at the night sky, feeling the quiet tension between familiarity and vastness. There is no requirement to resolve that tension. It does not need to become optimism or despair. It can simply be acknowledged. The universe is large, stars are numerous, human lives are brief. None of these statements negate the others. They describe different aspects of the same reality. As attention drifts back toward the present moment, toward the rhythm of breathing and the steady pull of gravity, the stars do not vanish. They fade from focus, not from existence. They remain above, shining old light, carrying history forward silently. You don't need to keep looking outward to honor that. Sometimes, the most complete relationship with the universe is a quiet one, where knowledge settles gently rather than demanding response. So here, under the same sky, with the same stars overhead, the question can be allowed to soften, not answered definitively, not dismissed, just set down carefully. The universe will continue expanding, stars will continue forming and fading, light will continue travelling across space and time, and on Earth, people will continue living small, intricate lives, occasionally looking up, occasionally wondering, always situated somewhere specific. Nothing more is required, and from this grounded place, rest comes a little more easily, knowing that the vastness above does not press down, but simply exists, patient and indifferent, while life continues quietly below.